Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the universe slows down just enough for us to wander through it together. Tonight, we're drifting far beyond planets, beyond stars, beyond even the familiar spiral arms of the Milky Way, towards something enormous and strangely quiet. We're going to explore what really happens when a galaxy dies. Now, that may sound dramatic at first. Galaxies seem eternal after all, immense cities of stars turning slowly through the dark for billions upon billions of years. They appear so stable, so permanent, that it's easy to imagine them lasting forever, quietly spinning long after everything else has faded away. And yet, galaxies do not live forever. Even the grandest galaxies in the universe, systems containing hundreds of billions of stars, eventually begin to change. Their bright nurseries fall silent, their glowing spiral arms start to fade. The steady birth of new stars slows down, weakens, and finally stops altogether. Over unimaginable stretches of time, these giant islands of light grow older, dimmer, colder, and quieter. A galaxy, it turns out, can age. It can starve. It can slowly lose the very thing that once made it alive. And perhaps the strangest part is this. Galactic death is rarely violent in the way people imagine. Not usually. There are explosions, certainly. Black holes throwing out enormous jets of radiation. Stars colliding. Entire galaxies crashing together. But the actual death of a galaxy is often far calmer than that. It is usually a very long exhaustion, a fading, a gradual running out of possibilities, rather like a city where fewer and fewer children are born each year until one day the streets are still there. The buildings remain, the lights continue glowing in some windows, but something essential has quietly changed. The future of the universe may not be fire or chaos. It may simply be silence arriving very slowly. And before we continue, I'd love to ask you something. Where in the world are you listening from tonight? Maybe you're under blankets while rain taps softly against the window. Perhaps you're lying awake in a quiet apartment while the rest of the city sleeps. Or maybe it's early morning where you are, and the sky's only just beginning to brighten. And what time is it for you right now? Fitting, really. A conversation about dying galaxies happening during one small moment in your own timeline. Somewhere on a moving planet, orbiting an ordinary star inside a galaxy that is itself already aging. If you find this journey soothing or interesting, or simply a pleasant way to slow your thoughts for a while, I'd be ever so grateful if you liked the video and maybe subscribed. It helps this quiet little corner of the internet keep drifting outward toward other curious minds who might need a peaceful place to rest for a bit. Now then, let's settle in. Because to understand how a galaxy dies, we first need to understand what a galaxy actually is. When most people picture a galaxy, they imagine something simple. Usually a beautiful spiral shape floating in darkness, perhaps like the famous photographs of the Milky Way or Andromeda. Bright arms curling outward gracefully like cosmic pinwheels. But a galaxy is not really an object in the ordinary sense. It is closer to an ecosystem. A galaxy contains stars, certainly, but also gas, dust, magnetic fields, radiation, black holes, dark matter, star clusters, stellar corpses, rogue planets, and enormous invisible structures stretching far beyond what telescopes can directly see. Everything inside it is interacting constantly. Stars are born from collapsing clouds of gas. Those stars eventually age and die, throwing material back into space. That material forms new stars. Black holes influence the motion of entire regions. Gravity slowly reshapes everything over billions of years. Nothing inside a galaxy is truly standing still. Even now, at this very moment, our own Milky Way is moving through space at roughly 2.1 million kilometers per hour relative to the cosmic background radiation. Entire star systems orbit the galactic center. Giant molecular clouds drift through spiral arms. ancient stars migrate gradually across the disk, and despite all this motion, galaxies can appear calm because the distances involved are so absurdly large. If the Milky Way were shrunk down to the size of the North America, individual stars would still be separated by thousands of kilometers. Space inside galaxies is mostly emptiness. That emptiness matters, because galaxies depend on very delicate balances. The most important balance of all is the balance between starbirth and resource consumption. A living galaxy is, in many ways, a galaxy still capable of making new stars. That may sound surprisingly simple, but it changes everything. Young galaxies are crowded with cold hydrogen gas, the raw material stars are made from. Under gravity, enormous clouds collapse inward. Regions become denser and hotter until nuclear fusion begins. A new star ignites. This process happened constantly in the early universe. Back then, galaxies were energetic places, chaotic, bright, productive. Some formed stars hundreds of times faster than the Milky Way does today. The universe itself was younger then too, hotter, denser, rich in fresh hydrogen left over from the Big Bang. In a sense, the cosmos had more fuel available and far more enthusiasm about using it. Modern galaxies are slower, older, more settled, and our Milky Way sits somewhere awkwardly in middle age. Astronomers estimate that the Milky Way currently forms about 1 to 2 solar masses worth of stars each year. That sounds impressive until you compare it to certain starburst galaxies producing hundreds of solar masses annually. Those galaxies are like enormous cosmic factories running day and night. The Milky Way, by comparison, is more like a quiet town where construction still happens occasionally, but nobody's really in a hurry anymore. Even so, stars continue forming here. Deep inside giant molecular clouds, gravity still gathers cold gas together. Protostars still ignite. Planetary systems still emerge. Somewhere inside the Milky Way tonight, entirely new suns are turning on for the first time. But this process cannot continue forever, because every star formation event consumes gas. And gas, although abundant on human scales, is finite on galactic ones. Over billions of years, galaxies slowly use up the material needed to create future generations of stars. Worse still, certain events actively prevent new star formation altogether. Supernova explosions can blast gas outward. Supermassive black holes can heat surrounding material so intensely that it can no longer collapse into stars. Galactic collisions can trigger temporary bursts of star formation that burn through remaining fuel too quickly. A galaxy may die from starvation, or exhaustion, or internal violence, sometimes all three at once. The fascinating thing is that astronomers can actually observe galaxies in different stages of this process right now. Some galaxies are young and vibrant, full of blue stars and active star-forming regions. Others appear reddish and quiet, populated mostly by old stars nearing the later stages of their lives. These older galaxies are sometimes called red and dead, which sounds rather harsh, honestly, like a failed restaurant review written by an astrophysicist. But the nickname exists for a reason. Young stars burn hot and blue. Old stellar populations tend to appear redder because the massive blue stars die relatively quickly, leaving behind smaller, cooler stars that survive much longer. So when astronomers observe a galaxy glowing mostly red with little evidence of new star formation, they know something important has changed there. The cycle has slowed down, perhaps nearly stopped. And what's remarkable is how gradual this can be. Human civilizations rise and fall in mere thousands of years. Species appear and disappear over millions. Galaxies evolve over billions. Their deaths are almost impossible for the human mind to emotionally grasp because they happen so slowly. Imagine watching a forest age, but every second equals 1 million years. Trees would bloom and collapse like sparks. Mountains would rise and erode before your eyes. Entire oceans would appear and vanish. Galactic time operates on scales even beyond that. which means the Milky Way itself is already changing in ways no human could ever notice directly. Some of the stars you see in the night sky are far older than Earth, others are comparatively young. Some regions of our galaxy are still fertile star-forming zones, while others have gone mostly quiet. The Milky Way is not one age, it is many ages layered together, and eventually those layers will shift further and further toward old age. But long before the last stars disappear, something else will happen. Our galaxy is going to collide with another one, and not just any galaxy. Andromeda, the enormous spiral galaxy currently drifting toward us from about 2.5 million light-years away. At first, that sounds terrifying. Two galaxies colliding feels like the kind of event that should instantly destroy everything. But because stars are so widely separated, most individual solar systems will pass through unharmed. The real effect happens on much larger scales. Gas clouds collide. Gravitational structures distort. Star formation surges violently. Black holes migrate toward each other. Over time, both galaxies lose their elegant spiral structures and merge into something larger, rounder, older, and calmer, a giant elliptical galaxy. The Milky Way will not simply fade quietly into darkness exactly as it is now. Its final middle-aged years will involve one last enormous transformation, and strangely enough, this is normal. Galactic collisions are common throughout the universe. In fact, many galaxies owe their current shapes to ancient mergers that happened billions of years ago. Some astronomers even suspect our own Milky Way consumed several smaller galaxies in the distant past. Evidence of those mergers still lingers in the motions of certain stars. Galaxies are not isolated forever. Gravity eventually pulls many of them together, which creates another curious truth about galactic death. Sometimes destruction creates temporary rebirth. When galaxies merge, gas compresses dramatically. New waves of star formation ignite. Entire regions blaze with newborn stars. For a while, the galaxy may actually become brighter and more active than before, but there's a cost. These bursts consume fuel rapidly. The merged galaxy often burns through huge amounts of remaining gas in relatively short cosmic periods. Eventually, the frenzy subsides, leaving behind a larger but older system with fewer resources left for the future. A final feast before the long quiet. And then there are the black holes. Every large galaxy appears to contain a supermassive black hole at its centre. The one inside the Milky Way is called Sagittarius, a star, and it contains about 4 million times the mass of our Sun. Which sounds enormous until you realise some galactic black holes contain billions of solar masses. These monsters influence entire galaxies. Normally many remain relatively calm, but under certain conditions they awaken. When enough gas falls inward, the region around the black hole becomes intensely bright. Matter heats to incredible temperatures while spiralling inward. Radiation blasts outward across space. These active galactic nuclei can become so energetic that they effectively sterilize star formation across huge distances. The galaxy's own centre begins working against it. Astronomers believe this may explain why many massive galaxies stop producing stars earlier than expected. Their central black holes become too effective at heating and disrupting the cold gas required for stellar birth. In other words, galaxies may partly engineer their own endings. The very structures created by their growth eventually interfere with future growth. There's something oddly biological about that. The universe often behaves less like machinery and more like ecology. Processes feed other processes. Growth changes environments. Stability creates new instabilities. Nothing remains frozen permanently. Even on cosmic scales. And perhaps that's what makes dying galaxies so strangely fascinating. Not merely the science itself, but the realization that impermanence exists everywhere. On Earth, living things age because energy and resources are limited. Stars age because fusion consumes fuel. Galaxies age because star formation cannot continue indefinitely. Even the universe itself appears headed toward gradual change on unimaginable timescales. Yet none of this is tragic in the human sense. The cosmos is not mourning these transformations. A galaxy does not fear death. It does not resist aging. It simply evolves according to the rules written into matter, gravity, energy, and time, and in a way that can feel unexpectedly calming. Because the night sky often appears so fixed and eternal that it creates the illusion of permanence. But permanence has never really existed anywhere. Not in biology, not in geology, not in stars, not even in galaxies. The universe is movement. Slow movement sometimes, but movement nonetheless. Right now, countless galaxies across the observable universe are quietly transitioning toward old age. Some already stopped forming stars billions of years ago. Others are still vibrant and active. Some are colliding, some are isolated, some are slowly being stripped apart by neighbouring galaxies and giant gravitational clusters. Every one of them has a story unfolding across deep time, and somewhere very far in the future, long after humanity is gone, after Earth itself no longer exists, after even the sun has died, the Milky Way's remaining stars will continue orbiting through a darker and quieter cosmos. Fewer new lights appearing, more old lights fading, the galaxy slowly settling into its final form. Step outside on a clear night, and it becomes very easy to understand why humans once believed the heavens never changed. The stars seem fixed, calm, reliable, ancient in a way that feels completely beyond ordinary life. Entire civilizations have risen, fought wars, built monuments, vanished into history, and still the constellations remain almost exactly where they were. Orion still stands in winter skies. The Milky Way still stretches overhead like pale fog. Distant galaxies continue glowing faintly through telescopes exactly as they did for our grandparents and their grandparents before them. From a human perspective, the universe appears remarkably stable, and honestly that illusion makes perfect sense. Human beings are creatures built for short timescales. We notice seasons because they happen quickly enough to affect crops and weather. We notice aging because it unfolds within decades. We notice mountains as permanent because they outlive civilizations, even though mountains themselves are temporary geological features slowly worn down by erosion. Galaxies exist on scales so enormous that the human brain instinctively classifies them as eternal. But eternal and extremely slow are not the same thing. That distinction matters. Because once astronomers began observing the universe carefully over long periods of scientific history, they discovered something surprising. Galaxies are not static objects frozen in time. They are changing constantly, just far too gradually for humans to perceive directly. In a strange way, galaxies resemble forests. If you stand in a forest for 5 minutes, it appears motionless. Trees seem fixed and permanent, but return over centuries and everything changes. Young saplings grow tall, old trees collapse, species migrate, rivers shift course, entire ecosystems evolve. The forest was never truly still. You are simply observing it too briefly. The same is true for galaxies. Take the Milky Way. At first glance it looks serene, a graceful spiral quietly turning through darkness. Yet inside it, stars are exploding every century or so. Giant clouds of gas are collapsing into new stellar systems. Black holes are feeding. Ancient stars are drifting into new orbits. Entire clusters are moving gradually across the galaxy. Even our own solar system is racing around the galactic center at roughly 828,000 kilometers per hour. And despite that enormous speed, it still takes about 230 million years to complete a single orbit around the Milky Way. Dinosaurs appeared and vanished during just one galactic year. That alone begins to explain why galaxies feel timeless to us. Their clocks move differently, not because time itself changes, but because the processes shaping galaxies unfold over intervals so vast that human history barely registers against them. Imagine watching a continent drift. Fingernails grow faster than tectonic plates move, yet continents absolutely do move. Mountains rise, oceans open, land masses collide. Earth's surface today looks nothing like it did 200 million years ago. Galactic evolution is slower still, which creates a peculiar psychological effect. The slower something changes, the more permanent it appears. That illusion shaped human civilization for most of history. Ancient cultures often viewed the heavens as symbols of perfection, precisely because they seemed unchanging. On Earth, everything decayed. Crops failed, empires collapsed, people aged, but the stars remained. The Greek philosopher Aristotle argued that the heavens must be fundamentally different from Earth because celestial objects appeared eternal and flawless. In his view, change belonged to the imperfect terrestrial world below, while the cosmos beyond the moon existed in a state of divine permanence. To be fair to Aristotle, the universe really does try very hard to look eternal. Even modern astronomy struggles emotionally with the scale of cosmic time. For example, consider the Andromeda Galaxy, the nearest large spiral galaxy to the Milky Way. Light from Andromeda takes about 2.5 million years to reach Earth. That means when you look at it tonight, you are not seeing Andromeda as it is now. You're seeing ancient light. That light began travelling toward Earth long before humans existed in their current form. While those photons crossed into galactic space, entire species evolved and disappeared on Earth. And yet Andromeda still looks almost exactly the same. Not because it hasn't changed, but because galaxies evolve slowly enough that even millions of years barely alter their overall appearance. This is one reason astronomy feels so strange compared to other sciences. Astronomers cannot usually watch cosmic events unfold in real time. They reconstruct them indirectly by observing objects at different stages. Imagine trying to understand human aging without ever seeing one person grow old. Instead, you only observe millions of different people frozen at various ages. Some are infants, some middle-aged, some elderly. By comparing them carefully, you infer how aging works. That is essentially how astronomers study galaxies. Some galaxies are young and chaotic, others are mature spirals, some are already old elliptical systems where star formation largely ended billions of years ago. The universe provides snapshots, astronomy assembles the story, and the story reveals something deeply important. Galaxies are temporary structures, enormous temporary structures certainly, long-lived beyond ordinary comprehension, but temporary nonetheless. The reason they seem eternal is partly because stars themselves live so long. Our Sun, for instance, will survive roughly 10 billion years total. It is currently about halfway through that lifespan. Red dwarf stars, the smallest and most common stars in the universe, can burn for trillions of years. Trillions. That word barely feels real. 1 trillion seconds equals over 31,000 years. $1 trillion budget sounds absurdly large because human minds are terrible at processing such scales. Now imagine trillions of years. Some red dwarfs alive today may continue shining long after nearly every other star in the cosmos has died. From a human perspective, such objects effectively are eternal. But galaxies are not merely collections of immortal stars hanging motionless in space. They are dynamic systems dependent on energy flow and material recycling. That changes everything. A galaxy stays vibrant only as long as it can continue creating new stars, and star formation depends on cold gas. This becomes the central issue in galactic aging. At the beginning of a galaxy's life, enormous reserves of hydrogen gas exist throughout the system. Gravity compresses portions of that gas into stars. Those stars eventually die and return some material back into space through stellar winds and supernova explosions. For a while, this creates a sustainable cycle, but not perfectly sustainable. Every generation of stars locks away some material permanently. Certain stars eject gas violently enough to push it outside the galaxy entirely. Black holes heat surrounding matter. Galactic collisions disturb delicate balances. Over immense timescales, the galaxy slowly loses efficiency, like an aging economy spending resources faster than it replenishes them. The Milky Way today already forms fewer stars than it once did. Billions of years ago, our galaxy was far more active. Star formation rates were higher, gas clouds were denser, massive blue stars lit enormous regions. Now things are calmer, more orderly perhaps, but also older. The spiral arms still glow beautifully, yet many regions of the galaxy are populated mostly by ancient stars formed long ago. Astronomers can actually map stellar ages across the Milky Way. Certain stars contain very low amounts of heavy elements, meaning they formed early in cosmic history before repeated generations of supernova explosions enriched the galaxy with metals like iron, oxygen, and carbon. Those old stars are survivors from another era, tiny fossils still orbiting through modern space. Some are over 12 billion years old, which means they formed before Earth existed. That realization quietly changes the night sky, doesn't it? Some stars overhead tonight were already ancient when the sun was born, and yet even they are temporary, because galaxies ultimately face another problem beyond simply running out of gas. Gravity itself slowly reshapes them. Over billions of years, galactic interactions become unavoidable. Small galaxies merge into larger ones. Spiral structures distort. Stellar orbits randomize. Central black holes grow. The elegant spiral appearance people associate with galaxies is not a permanent state. In fact, many astronomers suspect spiral galaxies represent only one phase in a much longer evolutionary story. Eventually, repeated mergers and declining star formation transform many galaxies into giant ellipticals. These systems contain huge populations of old stars but very little cold gas. No fresh stellar nurseries, no bright blue young stars, just aging stellar populations slowly fading over time. They are not dead in the cinematic sense. Nothing dramatic announces the moment. There is no giant cosmic alarm clock suddenly declaring the end. Instead, the galaxy gradually stops renewing itself, and perhaps that is why galactic death feels strangely unsettling compared to stellar death. A star dies visibly, explosively sometimes. Supernovae blaze across space with astonishing violence. Galaxies usually die quietly. The universe simply becomes less productive there, less fertile. Like a city where no children have been born for centuries. The buildings remain. Lights still glow in windows, but the future has stopped arriving. One fascinating example involves so-called quenched galaxies. These are galaxies where star formation ended unusually early. Some stopped producing stars when the universe was only a few billion years old. Astronomers still debate exactly why certain galaxies quenched so rapidly. In some cases, central black holes may have blasted away gas reservoirs. In others, collisions triggered huge bursts of star formation that exhausted fuel supplies prematurely. There are even galaxies drifting through clusters where hot intergalactic gas strips material away from them like wind tearing leaves from a tree. The universe can be surprisingly aggressive toward galaxies, and yet because these events unfold over enormous timescales, the results still appear calm to us. A dead galaxy often looks beautiful. That's the strange part. Massive elliptical galaxies glow with warm golden light. Their ancient stars create smooth, luminous halos stretching across hundreds of thousands of light years. They do not look ruined, they look peaceful. Which tells us something interesting about how humans emotionally interpret the cosmos. We instinctively associate beauty with vitality, but in astronomy, some of the most beautiful objects are already nearing the ends of their active lives. In fact, the universe we currently inhabit may exist during a particularly fortunate era for observation. This is something cosmologists occasionally point out with a mixture of excitement and existential discomfort. Right now, stars still form abundantly across the cosmos. Galaxies remain visible. The universe still contains energetic processes illuminating vast regions of space. Far in the future, things may become much darker. Eventually, galaxies beyond our local group will recede so far due to cosmic expansion that their light can no longer reach future observers. The night sky itself will empty gradually. Future civilizations, if any exist trillions of years from now, may see a universe containing only their own merged local galaxy surrounded by darkness. No visible evidence of the Big Bang, no distant galaxies. No rich cosmic web stretching across space. Just isolation. It's a peculiar thought. Humanity may exist early enough in cosmic history to witness the universe while it is still socially active, so to speak. Galaxies still crowd the heavens now. They will not always do so. And this helps explain another reason galaxies seem eternal. The universe itself is currently busy. Modern astronomy observes countless luminous systems because we live during an energetic cosmic period. The cosmos is only about 13.8 billion years old, which sounds ancient to us, but may actually represent a relatively youthful stage in the full lifespan of reality. Stars continue burning because hydrogen remains available. Galaxies continue evolving because gravity still gathers matter together. But entropy never stops working. Energy gradually spreads out. Useful structure becomes harder to maintain. Systems drift toward equilibrium. Galactic death is partly an expression of this larger universal trend. Not sudden destruction, gradual exhaustion. And yet despite all this, there's something deeply comforting about galaxies too. Their immense lifespans place human anxiety into perspective. A difficult week feels different when you remember some stars have existed for billions of years. Entire civilizations occupy less than a blink compared to galactic evolution. That perspective does not erase human problems, of course, but it changes their scale slightly. The universe is patient in ways humans cannot naturally comprehend. Galaxies drift slowly through darkness, changing almost imperceptibly. Even death there becomes stretched across spans so vast that it transforms from catastrophe into process. Perhaps that is the real reason galaxies feel eternal to us. Not because they truly last forever, but because their endings happen slowly enough to resemble permanence, the same way mountains seem permanent to people, or oceans, or forests. Everything appears eternal when viewed briefly enough, and in the case of galaxies, humanity has only just arrived to witness them at all. We are studying cosmic civilizations during one temporary phase of their existence, while many still shine brightly with young stars and rich supplies of gas, but eventually those supplies diminish. The great stellar factories slow, the blue light fades, and over unimaginable stretches of time, galaxies begin entering a quieter age where fewer and fewer new suns appear. Which raises the next question naturally. If star formation is the heartbeat of a living galaxy, what actually happens when that heartbeat begins to slow down? A galaxy can survive losing planets. It can survive exploding stars, wandering black holes, and even enormous collisions with other galaxies. But there is one thing it cannot survive forever: the loss of star formation. That is the true beginning of galactic old age, not destruction in the dramatic sense. Not fire raining through space or spiral arms suddenly tearing apart. The process is much quieter than that. A galaxy begins to die when fewer and fewer new stars are born each year. At first, almost nothing looks different. That's what makes it so fascinating. Imagine visiting a large city where the birth rate has slowly declined over generations. The streets still exist. Buildings remain standing. Lights glow in apartment windows. People still move through daily life. Yet beneath the surface, something important has changed. Schools begin closing. Entire neighborhoods grow older. Fewer young faces appear every year. The city continues functioning, but its future is shrinking. Galaxies experience something surprisingly similar. A young galaxy is crowded with cold gas clouds, mostly hydrogen, drifting through spiral arms like enormous invisible weather systems. Some of these clouds stretch for hundreds of light years, and contain enough material to form millions of stars. Inside them, gravity is always working patiently. Tiny irregularities develop. Certain regions become denser than others. As more material gathers, gravity strengthens further, pulling in additional gas. Temperatures rise, pressure increases. Eventually, deep inside the collapsing cloud, the core becomes hot enough for nuclear fusion to begin. A star ignites. For a galaxy, this process is life. And for billions of years after the Big Bang, the universe was astonishingly good at it. The early cosmos was full of raw hydrogen left behind from the universe's beginning. Galaxies were rich with cold gas. Star formation rates were dramatically higher than they are today. Some galaxies produce stars so rapidly that astronomers now call them starburst galaxies. These systems can create hundreds or even thousands of solar masses worth of stars every year. Compared to them, the Milky Way is almost sleepy. Our galaxy currently forms roughly 1 or 2 solar masses worth of stars annually. Respectable certainly, but nowhere near the frantic productivity seen in younger or more active systems. And even the Milky Way is slowing down. That's the important part. Star formation is not a permanent condition. A galaxy only continues making stars as long as 3 things remain true. It must possess enough cold gas, that gas must stay cool enough to collapse under gravity, and nothing can interfere too violently with the process. Over time, all 3 conditions become harder to maintain. The simplest problem is fuel consumption. Every new star permanently changes the galaxy's available resources. Some material eventually returns to space through stellar winds or supernova explosions, but not all of it. A significant amount remains locked inside stars, planets, white dwarfs, neutron stars, and black holes. Galaxies slowly spend their hydrogen reserves, not quickly by human standards, of course. Even at current rates, the Milky Way contains enough gas for billions more years of star formation. But billions in astronomy can sometimes mean already halfway done. And there's another complication. Not all gas inside a galaxy is useful for making stars. Temperature matters enormously. Cold gas collapses relatively easily because pressure remains low enough for gravity to dominate. Hot gas behaves differently. It expands. It resists collapse. It becomes difficult or impossible to compress into new stellar systems. This is where galaxies begin encountering serious trouble. As stars age and die, they inject energy back into their surroundings. Massive stars produce powerful stellar winds. Supernova explosions blast shockwaves through space at enormous speeds. Radiation heats nearby material. A galaxy's own stars slowly make the environment harsher for future star formation. It's a little like trying to grow delicate plants beside an increasingly active industrial zone. The irony is almost biological. Young stars help end the conditions that created them, and then there are supermassive black holes. For a long time, astronomers thought black holes were mostly passive objects sitting quietly in galactic centres. Dangerous nearby, certainly, but not particularly important on larger scales. That turned out to be very wrong. Modern observations reveal that supermassive black holes can influence entire galaxies. When enough gas falls toward one of these black holes, an accretion disk forms around it. Matter spirals inward, heats tremendously, and releases extraordinary amounts of energy. In some cases, these active galactic nuclei become brighter than all the stars in the surrounding galaxy combined. The black hole itself remains dark, oddly enough. It is the doomed material around it that shines, and what shining it does. Radiation floods outward across space. Jets erupt from the galactic center at nearly the speed of light. Nearby gas heats dramatically or gets blasted completely out of the galaxy. Astronomers now believe this process, called feedback, may be one of the main reasons massive galaxies stop forming stars. The black hole effectively sterilizes its own galaxy. It interrupts the cooling process required for gas clouds to collapse. In other words, galaxies can accidentally sabotage themselves. The larger and more active they become, the harder it becomes to continue producing future generations of stars. Some of the clearest examples appear in giant elliptical galaxies. These enormous systems often contain trillions of stars and exceptionally massive black holes at their centres. Yet despite their size, many produce almost no new stars at all. They possess plenty of material overall, but much of the gas is too hot and diffuse to collapse effectively. The galaxy becomes stuck in a kind of aging equilibrium, still glowing, still gravitationally stable, but no longer truly renewing itself. Astronomers sometimes describe these galaxies as quenched, a fascinating word really, as though star formation were a fire gradually deprived of oxygen, and in some sense, that's exactly what's happening. One particularly interesting discovery involves the colour of galaxies. Young star-forming galaxies often appear blue. That's because massive young stars burn extremely hot and emit large amounts of blue and ultraviolet light. These stars are brilliant but short-lived. Most survive only a few million years before exploding. Older galaxies appear redder. Once star formation slows or stops, those bright blue stars disappear relatively quickly, leaving behind longer-lived redder stars that dominate the galaxy's appearance. This allows astronomers to estimate galactic age visually. Blue usually means youthful activity. Red often signals old age. The universe itself contains an enormous population of these aging red and dead galaxies. Some stopped forming stars billions of years ago. And the remarkable thing is how ordinary they can look. No shattered spiral arms drifting dramatically through darkness. No giant cosmic warning signs. Many appear smooth, calm and elegant through telescopes. Galactic death is often aesthetically peaceful. That contrast between appearance and reality feels strangely human somehow. Things can look stable long after important internal changes have already happened. Another major factor in galactic aging involves environment. Galaxies rarely live entirely alone. Many exist inside clusters containing hundreds or thousands of neighbouring galaxies, immersed in extremely hot intergalactic gas. This environment can be brutal. As galaxies move through these clusters, pressure from surrounding gas can literally strip material away from them. Astronomers call this ram pressure stripping. Though honestly, it sounds more like something you'd use to clean stubborn stains from a driveway. The effect is dramatic. A galaxy travelling through dense cluster environments gradually loses its cold gas reservoirs. Long tails of stripped material trail behind it through space. Without fresh gas, star formation weakens. The galaxy slowly starves. Some galaxies experience this process so severely that they stop forming stars far earlier than they otherwise would have. Others lose gas through repeated collisions and mergers. Galactic collisions sound catastrophic, but because stars are separated by such huge distances, direct stellar impacts remain rare. The real violence happens between gas clouds. During mergers, enormous quantities of gas compress suddenly. This can trigger spectacular bursts of star formation. Entire regions blaze with newborn stars at astonishing rates. For a while, the galaxy appears more alive than ever. But these starbursts consume fuel rapidly. It's rather like spending decades worth of energy in one enormous celebration. Afterward, the galaxy may find itself exhausted. Gas depleted, future star formation crippled, one final blaze before decline. And perhaps the strangest aspect of all this is how invisible the process would feel from inside a galaxy. If human civilization somehow survived for billions of years inside the Milky Way, nobody would wake up one morning announcing that star formation had ended. The change would happen gradually across immense timescales. Fewer stellar nurseries would appear. Massive blue stars would become rarer. The galaxy's overall light would shift subtly redder over eons. Civilizations living through different cosmic eras might barely notice the transformation, because every generation accepts its version of the sky as normal. That idea has an oddly melancholy quality to it. the possibility that enormous change can happen slowly enough to feel invisible while it's occurring. Even now, astronomers believe the universe as a whole is forming stars far more slowly than it once did. This is one of the most important large-scale trends in cosmic history. Roughly 10 billion years ago, the universe experienced what astronomers call cosmic noon, the peak era of star formation. Galaxies everywhere produced stars at dramatically higher rates than they do today. The cosmos was busier then, brighter, more fertile. Since that era, star formation across the observable universe has declined significantly. The universe itself is aging, not dying exactly, not yet, but gradually becoming less productive, less energetic, more settled. In a sense, we live after the great cosmic rush. Most stars that will ever exist may already have formed, and while that sounds gloomy at first, it also means we inhabit a very interesting period of cosmic history. The universe still contains abundant stars, galaxies, and active processes. Night skies remain rich with light. Far in the future, things become quieter, much quieter. Eventually, star formation will cease almost entirely across most galaxies. Existing stars will continue shining for immense spans of time, especially small red dwarfs, but no substantial new generations will replace them. Galaxies will become populations of aging stars slowly drifting through expanding darkness. The phrase astronomers sometimes use is stellar senescence, galactic old age. And once you start thinking about galaxies this way, the night sky changes emotionally. The Milky Way no longer feels like a fixed backdrop. It becomes a living system passing through phases. Long ago, our galaxy was younger and more chaotic. Billions of years from now, it will be older and quieter. We happen to exist somewhere in between. Right now, the Milky Way still contains giant molecular clouds rich with cold hydrogen. The Orion Nebula still forms stars. Dense regions still collapse under gravity. New planetary systems still emerge from disks of dust and gas. Somewhere in our galaxy tonight, planets are forming around stars so young they have not fully stabilized yet. And somewhere else, ancient stars older than Earth continue their slow orbits around the galactic center. The Milky Way contains many different cosmic eras simultaneously, but the balance is shifting, slowly, almost imperceptibly. The galaxy consumes more of its future with every passing age, and one day, although unimaginably distant from us now, the last major star-forming regions of the Milky Way will finally go dark. No more stellar nurseries, no more bright young blue stars, only aging stellar populations remaining. The galaxy will still exist then, certainly. Its stars will continue orbiting. White dwarfs, neutron stars, and black holes will linger for lengths of time difficult to describe meaningfully. But something essential will have ended. The Milky Way's ability to renew itself. And oddly enough, that may be the clearest definition of galactic death we have. Not destruction, not disappearance, simply the moment when no truly new light arrives anymore. If star formation depends entirely on cold gas, what exactly happens when a galaxy finally begins running out of it? If stars are the visible lights of a galaxy, then gas is the hidden bloodstream that keeps everything alive. Take away the gas and a galaxy slowly loses its future. That may sound surprising at first because galaxies look overwhelmingly full of stars. Bright spiral arms, glowing cores, enormous clusters scattered through space. When people imagine galaxies dying, they often picture stars exploding or black holes swallowing everything whole. But galaxies are not sustained by existing stars. They are sustained by the ability to create new ones, and that ability depends almost entirely on cold hydrogen gas. Without it, the great cycle that powers galactic evolution begins to fail. At first, the process is subtle. A galaxy does not suddenly wake up empty one morning. Gas disappears gradually over billions of years through a combination of consumption, heating, ejection, and disruption. The galaxy keeps functioning for a very long time afterward, because stars themselves survive much longer than the gas clouds that form them. That distinction is important. A galaxy can stop making stars long before it stops shining. In fact, some galaxies we observe today probably exhausted most of their star-forming fuel billions of years ago, yet they still glow beautifully across space because old stars continue burning. It's a bit like a city surviving on an aging population long after new generations stopped arriving. The lights remain on for quite a while. To understand what happens when gas disappears, we first need to appreciate how astonishingly important gas really is inside galaxies. Most of the visible matter in a galaxy is not actually stars. A tremendous amount exists as diffuse clouds spread across interstellar space. Some regions are hot and thin. Others are dense, cold, and rich enough to collapse under gravity into future stellar systems. These cold molecular clouds are the real engines of galactic life, and they are enormous. The Orion Molecular Cloud Complex, one of the nearest star-forming regions to Earth, stretches across hundreds of light years and contains enough material to produce thousands of stars. Inside these clouds, gravity constantly competes against pressure and temperature. When conditions remain cool enough, gravity wins. Dense knots form, collapse accelerates, protostars ignite. But once the supply of cold gas diminishes, fewer regions can collapse successfully. Star formation begins slowing down. The galaxy enters a quieter age. One way this happens is surprisingly straightforward. The galaxy simply uses up its available fuel. Stars are incredibly efficient at locking away matter for enormous spans of time. A small red dwarf may burn hydrogen so slowly that it survives for trillions of years. Material trapped inside such stars effectively disappears from the galactic recycling process for timescales longer than the current age of the universe. Larger stars return some material through stellar winds and supernova explosions, but not perfectly. Every generation leaves some matter permanently unavailable. Over enough time, the galaxy's gas reserves shrink. Yet simple fuel consumption alone is not usually enough to fully explain galactic death. Many galaxies still contain substantial amounts of gas even after star formation slows dramatically. The real issue is often temperature. Cold gas forms stars, hot gas does not, and galaxies become very good at heating their own environments. Massive stars produce intense ultraviolet radiation that ionizes nearby hydrogen. Supernova explosions generate enormous shock waves capable of stirring and heating interstellar material across huge distances. Then there are active galactic nuclei powered by supermassive black holes. These may be the ultimate cosmic troublemakers. When matter falls toward a central black hole, tremendous energy gets released into surrounding space. Jets blast outward. Radiation floods the galaxy. Huge quantities of gas become too energetic to collapse into new stars. Astronomers believe some galaxies effectively suffocate themselves this way. The black hole prevents cooling. Without cooling, no collapse occurs. Without collapse, no new stars form. One of the strange ironies of cosmic evolution is that the structures helping galaxies grow larger can also contribute to shutting future growth down entirely. And once gas becomes too hot and diffuse, recovering from that state can be difficult. A galaxy may still contain billions of solar masses worth of material, yet much of it remains unusable for star formation because the conditions are wrong. Imagine trying to make snowballs during a heat wave. The ingredients technically exist, but the environment no longer cooperates. Some galaxies lose gas more violently. In galaxy clusters, enormous amounts of superheated plasma fill the space between galaxies. As galaxies travel through this environment, pressure strips gas away from them. The effect can look almost biological through telescopes. Long tendrils of material trail behind galaxies like cosmic jellyfish drifting through dark oceans. Astronomers sometimes call these jellyfish galaxies, which is honestly one of the more charmingly unsettling terms in astrophysics. The stripped gas often becomes completely unavailable for future star formation inside the galaxy itself. The galaxy is slowly bled dry by its environment, and then there are galactic collisions. At first glance, mergers might seem like they should replenish gas problems by combining the resources of multiple galaxies. Sometimes they do temporarily trigger enormous starbursts, but those bursts consume fuel at astonishing rates. Two spiral galaxies collide, gas clouds compress violently. Star formation surges. Massive blue stars appear everywhere. For a while, the merged system becomes incredibly active and bright, but the frenzy cannot last forever. Eventually, much of the remaining gas gets exhausted, heated, or blasted away. The galaxy settles into a quieter elliptical form with far less capacity for future star formation. A brief period of abundance followed by long decline. In a way, galaxies can age from overactivity as much as from scarcity. One particularly fascinating example involves the Milky Way itself. Our galaxy still possesses significant reservoirs of gas. Star formation continues, especially inside spiral arms where density waves help compress interstellar clouds. The Orion Nebula remains an active stellar nursery. New planetary systems continue forming across the galaxy. But compared to the Milky Way's earlier history, things are calmer now. Billions of years ago, star formation rates were likely much higher. The galaxy contained more cold gas and experienced more energetic interactions. Today the Milky Way appears relatively mature, not dead, not even especially old by galactic standards, but no longer youthful either. Astronomers suspect our galaxy may continue forming stars for several billion more years, especially once the future collision with Andromeda redistributes gas and triggers additional bursts of activity. Even so, the long-term trend remains unavoidable. Eventually, available cold gas declines, and once that happens, the character of the galaxy changes fundamentally. The first visible sign is usually colour. Young galaxies glow blue because massive hot stars dominate their light. These stars burn brightly but die quickly, often within only a few million years. Once star formation slows, those blue stars disappear relatively fast on cosmic timescales. Older, redder stars remain. The galaxy gradually shifts in appearance. Blue fades into gold. Gold slowly deepens toward red. Astronomers can estimate galactic activity partly through this colour transition. Some galaxies occupy what researchers call the Green Valley, an intermediate stage between active blue star-forming galaxies and quiet red elliptical systems. The name sounds oddly peaceful, doesn't it? Like a retirement community for galaxies, and honestly, in some sense, that is exactly what it represents. A galaxy transitioning toward old age. What's especially interesting is that many dead galaxies still contain astonishing numbers of stars. Some giant ellipticals contain trillions. The problem is not the absence of stars, it is the absence of youth. No fresh stellar generations emerge to replace the aging population. Over time, the galaxy becomes dominated by long-lived, low-mass stars. Bright massive stars vanish. Nebulae become rarer. Supernova rates decline. The overall structure grows calmer and dimmer, and perhaps the strangest thing of all is how stable this quiet phase can become. Once major star formation ends, galaxies may remain structurally intact for unimaginable periods. Stars continue orbiting through the galactic potential. Black holes persist. White dwarfs cool gradually. Red dwarfs keep burning. Galactic death is not immediate disappearance. It is more like biological aging stretched across cosmic timescales. The active reproductive phase ends first. The system itself lingers much longer afterward. There is something almost haunting about imagining the far future of a gas-depleted galaxy. Picture the night sky from a civilization living there trillions of years from now. No bright blue stars illuminating spiral arms. Few glowing nebulae where new suns are born. Mostly ancient red dwarfs, dim stellar remnants, and darkness between them. The galaxy still exists, but its era of creativity has ended. No new solar systems emerging. No fresh stellar populations lighting the dark. Just old survivors continuing their long orbits through increasingly quiet space. and the wider universe becomes quieter too. This is important because galaxies do not age independently from the cosmos around them. The universe itself evolves. Right now, galaxies can still occasionally acquire fresh gas through mergers or intergalactic inflows. But cosmic expansion gradually reduces these opportunities. Over immense timescales, galaxies become increasingly isolated. Resources stop arriving. Interactions become rarer. The universe slowly transitions from a crowded, energetic place into something more sparse and settled. In a younger cosmos, gas moved more freely between galaxies. Interactions were common. Matter remained abundant and relatively easy to compress into stars. The modern universe is already less fertile than it once was. Future epochs will be quieter still. One way astronomers study this process involves observing distant galaxies at different stages of cosmic history. Because light takes time to travel, telescopes effectively function as time machines. A galaxy observed 10 billion light-years away appears as it existed 10 billion years ago. And what astronomers consistently find is remarkable. The ancient universe formed stars far more aggressively than the present-day universe. Galaxies back then looked messier too, more turbulent, more chaotic, more crowded with gas. Today's cosmos feels comparatively mature, like arriving late to a party after most guests have already gone home. And eventually the party ends entirely. No major reservoirs of cold gas remain. Star formation effectively ceases. The great stellar factories shut down one by one across cosmic history. Still, there's an odd comfort in the slowness of all this. Human beings often fear endings because our endings happen quickly. Individual lives are short. Civilizations can collapse within generations. Galactic endings are different. A galaxy fades so gradually that entire intelligent species might rise and disappear during phases barely noticeable on cosmic scales. The Milky Way itself will survive vastly longer than Earth, long after the Sun expands into a red giant, long after our planet becomes uninhabitable, long after humanity, whatever form it may take then, either vanishes or moves elsewhere. The galaxy will continue drifting through space, older, quieter, still luminous in places, and eventually, once the gas finally dwindles beyond recovery, the last true stellar nurseries will disappear. At that point, something deeply important changes in the character of the galaxy, not because stars stop existing, but because birth itself has stopped. And once no new stars arrive, all remaining light belongs to aging survivors slowly moving toward their own endings. If galaxies can no longer create new stars, what happens to the old stars already living inside them? By the time a galaxy stops forming new stars, it has already changed profoundly. The great clouds of cold hydrogen that once drifted through its spiral arms have mostly vanished or become too hot to collapse. Bright stellar nurseries grow rare. The galaxy settles into a quieter rhythm. But the story is not over. Far from it. Because galaxies do not go dark immediately after star formation ends. In fact, some continue glowing for trillions of years afterward. The reason is simple. Stars themselves can live for extraordinarily long periods of time, and once no new stars are born, the future of the galaxy becomes entirely dependent on the stars already there. This creates a fascinating transition in cosmic history. A galaxy moves from an era defined by creation to one defined by survival. The younger stars disappear first. That may sound backward initially, but massive stars live the shortest lives. The brightest stars in the universe burn through their fuel with astonishing speed. Some survive only a few million years before exploding as supernovae. Compared to smaller stars, they are extravagantly wasteful. Imagine two campfires. One burns huge and bright, throwing sparks everywhere, devouring wood rapidly. The other burns quietly and steadily through the night. Massive stars are the first kind. Red dwarfs are the second. Once star formation stops, the galaxy's remaining population immediately begins aging unevenly. The giant blue stars vanish quickly, and their disappearance changes everything visually. Young galaxies are filled with bright hot stars that emit enormous amounts of blue and ultraviolet light. These stars dominate the appearance of spiral arms and active star-forming regions. Without replacement generations, they die out relatively fast. Supernovae continue for a while, but each explosion removes another member of the galaxy's youthful population. Over time, the galaxy grows redder, calmer, older-looking. Astronomers can actually trace this transition across the universe. Galaxies dominated by young stars appear blue. Galaxies populated mostly by old stellar survivors appear yellow, orange, or red. The change is not merely cosmetic. It reflects a completely different phase of galactic existence. During active star formation eras, galaxies are dynamic ecosystems. Giant molecular clouds collapse continuously. New stars appear. Planetary systems emerge. Massive stars explode and enrich surrounding space with heavier elements. Once that process ends, the galaxy becomes more like a cosmic retirement community. Existing stars continue their lives, but very little truly new appears anymore. The remarkable thing is how long this quieter phase lasts. The future belongs to the small stars. Right now, when humans look at the night sky, our attention naturally focuses on bright stars because they are easiest to see. Sirius, Vega, Rigel, Betelgeuse. These luminous giants dominate human mythology and astronomy alike, but they are not typical stars. Most stars in the universe are small red dwarfs, tiny, cool, dim compared to the sun, and unbelievably patient. A red dwarf burns hydrogen so slowly that many will survive for trillions of years, not billions, trillions. That means not a single red dwarf has ever fully died naturally because the universe itself is still far too young. Every red dwarf ever formed still exists today. Some astronomers suspect these stars will become the last ordinary luminous objects remaining in the far future cosmos. And this has profound implications for dying galaxies. Once star formation stops, galaxies gradually become dominated by red dwarfs because almost everything else dies sooner. Massive stars explode quickly. Medium-sized stars like the Sun eventually expand into red giants and leave behind white dwarfs. But red dwarfs simply continue burning, quietly, steadily. For lengths of time so enormous they almost stop feeling meaningful. Imagine standing beside a candle that burns for longer than mountains exist, longer than galaxies actively form stars, longer than current cosmic history itself. That is roughly what a red dwarf represents. In the far future of a dead galaxy, these small stars become the primary surviving sources of light. The galaxy dims, but extremely slowly. At first, there are still plenty of sun-like stars around. Civilizations, if any exist, might continue orbiting stable stars for immense spans of time. Yet gradually larger stars vanish one by one. The galaxy's character changes subtly. Bright blue regions disappear entirely. Supernova explosions become rare events. Nebulae fade. The night sky itself evolves. Future observers living trillions of years from now would see a very different cosmos from ours. Their skies would lack many of the brilliant young stars familiar to modern astronomy. Instead, the heavens would glow mostly with dim, red points scattered across darkness. Ancient survivors, and eventually even the sun-like stars, disappear. Our own sun, for example, has about 5 billion years of stable life remaining. After exhausting hydrogen in its core, it will expand into a red giant large enough to engulf Mercury and probably Venus. Earth's fate remains somewhat uncertain, though pleasant is definitely not among the leading possibilities. Afterward, the Sun will shed its outer layers and leave behind a white dwarf. A white dwarf is one of the strangest objects in astrophysics. It contains roughly the mass of a star compressed into something about the size of Earth. Matter there behaves bizarrely. A teaspoon of white dwarf material would weigh tons on Earth. Yet white dwarfs no longer produce energy through fusion. They shine only because they remain hot from previous stages of stellar evolution. They are cooling embers. And in the future of dead galaxies, white dwarfs become incredibly common. Eventually, most ordinary stars end this way. The galaxy fills with stellar remnants, white dwarfs, neutron stars, black holes, a growing population of cosmic corpses orbiting through increasingly quiet space. Still, the transition remains extraordinarily gradual. That's the important thing to remember about galactic death. It does not resemble destruction in films where everything collapses at once. The galaxy ages layer by layer. Different stellar populations vanish on different timescales. Massive stars disappear first, then stars like the Sun. Finally, trillions of years later, the red dwarfs themselves begin approaching the ends of their lives. And because no red dwarf has died naturally yet, astronomers must model their future theoretically. Current calculations suggest many will eventually become blue dwarfs late in life, briefly growing hotter and brighter before ending as white dwarfs without dramatic explosions. The far future universe may therefore contain strange periods where ancient dying red dwarfs become unexpectedly luminous again for a while. Even at the end, stars remain complicated. One fascinating consequence of all this involves planetary systems. When galaxies stop forming stars, no major new planetary systems appear either. Existing planets continue orbiting their stars, but the creation of fresh worlds effectively ceases. This means the inventory of habitable environments becomes fixed. No new Earth-like planets arrive later to replace those lost over time. The galaxy enters a finite era of planetary survival. Some systems remain stable astonishingly long. Red dwarf stars especially may host planets for trillions of years, vastly longer than Earth's habitable lifespan around the Sun. Hypothetically, if intelligent civilizations adapted to such systems, life could persist deep into the future of dying galaxies. Though the universe surrounding them would grow increasingly dark and isolated, and isolation becomes one of the defining features of cosmic old age. As galaxies consume their last generations of stars, the wider universe continues expanding. Distant galaxies drift farther away. Over immense timescales, most become unreachable even at light speed because space itself expands too rapidly between them. Future civilizations may eventually see only their own local galaxy, while everything else vanishes beyond the observable horizon. Imagine looking into the night sky and seeing no other galaxies at all. No Andromeda, no distant spirals, no rich cosmic web stretching across billions of light years. Just your own ancient galaxy surrounded by darkness. Astronomers in that era might struggle even to discover the Big Bang because most evidence for cosmic expansion would have disappeared. In a peculiar way, humanity exists during one of the best possible periods for observing the universe. The cosmos is still active enough to reveal its history. That will not always be true. Inside dead galaxies, stellar encounters also become increasingly important over very long time scales. Stars continue orbiting the galactic center, but gravity slowly alters their trajectories through countless weak interactions. Occasionally stars pass relatively near one another. Planetary systems destabilize. Rogue planets drift loose into interstellar darkness. Some stars may even be ejected from the galaxy entirely. Galactic structure itself gradually loosens over immense periods. Even after star formation ends, gravity continues quietly reshaping everything. And then there are the black holes. Whenever massive stars explode, they sometimes leave black holes behind. Over trillions of years, dead galaxies accumulate huge populations of these invisible remnants. Most drift silently through space, detectable only through gravitational influence. The galaxy becomes increasingly populated by dark objects. Not because black holes suddenly take over dramatically, but because luminous stars slowly disappear while black holes persist. This creates an unsettling shift in cosmic demographics. The visible universe we know today is temporary partly because luminous stars are temporary. Future galaxies may contain far more mass in stellar remnants, than in actively shining stars. The light gradually loses the statistical battle, yet even then the process remains deeply slow. That slowness changes the emotional feeling of galactic death. Human beings instinctively associate endings with urgency. A collapsing building, a dying fire, a fading heartbeat. Galactic endings resemble none of these. They are patient beyond comprehension. A civilization could rise, flourish for millions of years, vanish completely, and the galaxy itself might barely change during that interval. There is something oddly peaceful about that scale. Not because cosmic aging is cheerful exactly, but because it removes panic from the equation. The universe does not rush toward its endings. It drifts, and the last generations of stars embody that perfectly. Picture a far future galaxy trillions of years from now. No bright spiral arms remain. No giant blue stars illuminate stellar nurseries. Mostly red dwarfs continue glowing softly across enormous darkness. Between them drift white dwarfs cooling slowly over unimaginable spans. Neutron stars rotate quietly. Black holes wander invisibly through old stellar halos. The galaxy still exists, still gravitationally bound, still slowly evolving. But its energetic youth belongs entirely to history. And eventually even those enduring red dwarfs will begin disappearing too. The last ordinary stars in the universe will not explode dramatically in synchronized finales. They will simply exhaust their fuel one by one across spans so vast that words like future almost lose meaning. The cosmos grows quieter incrementally. For most of human history, black holes would have sounded like something invented purely to frighten astronomers. Invisible regions of space so dense that not even light can escape them. Objects capable of swallowing stars. Places where gravity becomes so extreme that our ordinary understanding of physics begins to break down. And yet, despite all their strange reputation, black holes are not usually the villains people imagine. Most are surprisingly quiet. If the Sun were magically replaced with a black hole of equal mass, Earth would continue orbiting almost exactly as it does now. We would certainly freeze to death rather quickly, which is admittedly not ideal, but we would not get sucked dramatically into darkness like spaghetti spiraling down a cosmic drain. Gravity at large distances depends on mass, not personality. Black holes simply concentrate that mass into astonishingly tiny regions. Still, there is one category of black hole that genuinely deserves its intimidating reputation: supermassive black holes. These are the giants lurking in the centres of galaxies. And unlike ordinary stellar black holes formed from dying stars, supermassive black holes contain millions or billions of times the mass of the Sun. Every major galaxy we have studied carefully appears to contain one. The Milky Way's central black hole, Sagittarius A star, holds roughly 4 million solar masses. Large by human standards, certainly, though rather modest compared to some monsters elsewhere in the universe. The black hole at the centre of the galaxy Messier 87 contains around 6.5 billion solar masses. That is not a typo. Trying to emotionally process numbers like that is difficult, because human intuition evolved for forests, weather and social groups, not billion solar mass gravity wells sitting at the centres of galaxies. For a long time, astronomers assumed these black holes mostly sat quietly in galactic cores, occasionally swallowing unlucky stars but otherwise remaining relatively unimportant on larger scales. Then observations started revealing something extraordinary. Supermassive black holes can control the fate of entire galaxies, not metaphorically, literally. In some cases, they can help shut star formation down across enormous regions of space. And the strange part is that black holes themselves are not actually producing the damage directly. The real trouble comes from everything surrounding them. A black hole feeding actively becomes one of the brightest phenomena in the universe. That sounds completely backward at first. After all, black holes are famous specifically because light cannot escape them. But before matter crosses the event horizon, It spirals inward through what astronomers call an accretion disk. Picture water circling a drain, except the water is made of superheated plasma moving at enormous speeds around a gravitational abyss. As material compresses and rubs together inside the disk, temperatures rise tremendously. Friction and magnetic forces generate extraordinary amounts of radiation. The region around the black hole becomes dazzlingly bright, sometimes brighter than the entire galaxy surrounding it. These active systems are called quasars, or active galactic nuclei depending on their properties. And they are astonishingly violent places. Jets erupt outward from the galactic centre at nearly the speed of light. Radiation floods surrounding space. Shockwaves travel through interstellar gas. A feeding supermassive black hole can release more energy than billions of stars combined, and this is where galaxies begin getting into trouble. Remember, star formation depends on cold gas. Cool gas collapses under gravity into dense clouds capable of igniting fusion. Hot gas resists collapse. A galaxy filled with overheated gas struggles to form new stars, which means a sufficiently active black hole can slowly poison the conditions required for future stellar birth. Astronomers call this process feedback. The name sounds oddly polite considering the scale involved. What it really means is that the black hole begins reshaping the entire galaxy around it. Jets from active black holes can punch through galactic gas like enormous cosmic blowtorches. Radiation heats surrounding material across huge distances. In some galaxies, outflows driven by black hole activity actually eject gas completely into intergalactic space. The galaxy loses the raw material required for future generations of stars. Its future gets blasted away. One of the great discoveries of modern astrophysics is that galaxies and their central black holes appear deeply connected. The mass of a galaxy's central bulge correlates closely with the mass of its supermassive black hole. Somehow these vastly different scales influence each other, and astronomers increasingly suspect feedback is the reason. As galaxies grow, their black holes grow too. Eventually the black hole becomes energetic enough to interfere with further galactic growth. The galaxy effectively regulates itself through violence. There's something strangely ecological about that process. Too much activity eventually limits future activity. Some of the clearest examples appear in giant elliptical galaxies. These systems often contain enormous black holes surrounded by hot gas halos stretching hundreds of thousands of light years. Yet despite possessing huge amounts of material overall, they form relatively few new stars. The gas remains too hot and turbulent to collapse effectively. The black hole keeps the galaxy in a kind of cosmic retirement, still luminous, still structurally stable, but no longer youthful. One particularly fascinating observation involves giant cavities discovered in hot galactic gas. In some clusters, astronomers observe enormous bubbles carved out by black hole jets. These cavities are gigantic beyond ordinary imagination. Some stretch across distances larger than entire galaxies. The jets inflate them slowly, pushing surrounding gas outward, while injecting tremendous energy into the environment. And because the gas stays hot, it cannot easily condense into new stellar nurseries. The black hole becomes an anti-star machine. Instead of creating new generations, it suppresses them. The irony here is remarkable. Black holes are often imagined as cosmic destroyers consuming matter endlessly. But the real long-term damage may not come from swallowing stars directly. It comes from preventing future stars from ever forming in the first place. A galaxy can survive losing individual stars and cannot remain vibrant indefinitely once stellar birth stops entirely. Even the Milky Way may experience periods like this eventually. Right now, Sagittarius A star is relatively calm. Our central black hole emits comparatively little radiation because not much matter currently falls into it. But that has not always been true. Evidence suggests the Milky Way's core was likely far more active in the past. Astronomers have discovered giant structures called the Fermi bubbles, extending above and below the galactic centre. These enormous gamma-ray emitting lobes may be remnants of earlier black hole activity millions of years ago. At some point, Sagittarius A star probably fed much more aggressively than it does today, and in the future it may awaken again, especially during the eventual collision between the Milky Way and Andromeda. That future merger will dramatically disrupt both galaxies. Gas clouds will collide, matter will funnel toward the centre. The supermassive black holes of both galaxies will eventually spiral together and merge. Before they do, however, each black hole may enter active feeding phases. The centre of the future merged galaxy could become extraordinarily bright and violent for a time. Entire regions might experience intense radiation fields. Huge quantities of gas may heat or get expelled outward. Ironically, one final burst of galactic activity could help ensure the galaxy's later quietness, a farewell celebration that burns through remaining fuel. And once the black hole settles down afterward, the galaxy may emerge older, rounder, and far less capable of forming new stars. Astronomers believe many giant elliptical galaxies probably formed through exactly this kind of process. Ancient mergers followed by black hole-driven feedback gradually shutting stellar birth down. The galaxy survives, but its fertile years end. One particularly unsettling aspect of supermassive black holes is how invisible they often are unless feeding actively. The black hole itself emits no light. You notice its influence indirectly through surrounding motion and radiation. This means entire galaxies can be shaped by objects fundamentally hidden from ordinary observation, a silent engine controlling stellar futures from the centre. There's something almost mythological about that. Ancient civilizations often imagined invisible forces governing the heavens. Modern astronomy replaced mythology with physics, yet the universe somehow remains just as strange. Invisible dark matter structures shape galaxies gravitationally. Invisible black holes regulate star formation. Huge portions of cosmic evolution happen through things we cannot observe directly with human eyes, and over immense timescales, black holes become increasingly important because luminous stars gradually disappear. This shifts the balance of the galaxy. Young galaxies are dominated visually by stellar activity. Bright stars define them, nebulae glow, supernovae erupt. Old galaxies become quieter, the stars age, and slowly the black holes inherit more of the future, not because they suddenly multiply dramatically, but because everything else fades first. A dead galaxy trillions of years in the future may contain enormous populations of black holes drifting invisibly through dark stellar halos. Supermassive black holes remain at the centres. Stellar black holes orbit throughout the galaxy. White dwarfs cool. Neutron stars spin more slowly. Red dwarfs continue their patient burning. The visible universe gradually loses its battle against darkness. Yet even then, black holes are not truly immortal. That realization surprises many people. For decades, black holes were imagined as eternal cosmic prisons from which nothing could ever escape. Then physicist Stephen Hawking changed the picture. According to quantum mechanics, black holes should slowly lose energy through what is now called Hawking radiation. The process is incredibly slow for large black holes. A stellar black hole would take vastly longer than the current age of the universe to evaporate significantly. Supermassive black holes survive even longer. Numbers become almost absurd here. Some may persist for periods measured in googles of years. A google, just for reference, is one followed by 100 zeros. Human language begins failing slightly at these scales. Still, the key point remains. Even black holes eventually fade. The universe allows no permanent winners, not stars, not galaxies, not even the enormous gravitational monsters at galactic centres. And perhaps that is what makes supermassive black holes so fascinating within the story of galactic death. They are not merely destroyers, they are transitional forces. They help move galaxies from energetic youth toward quieter old age. A galaxy filled with active star formation behaves differently from one dominated by ancient stars and central black hole feedback. The black hole does not usually kill the galaxy suddenly. Instead, it changes the conditions required for renewal. It turns tomorrow into a harder place for stars to exist. And because the process unfolds over billions of years, the galaxy itself may continue looking majestic long after its future has already been quietly compromised. That idea feels strangely familiar on human scales too. Sometimes systems appear strongest right before the conditions supporting them begin disappearing underneath. Galaxies simply perform this transformation on cosmic timescales. The truly astonishing thing is that all of this happens inside structures so large the human mind struggles to picture them properly. Entire stellar civilizations may rise and vanish while black hole feedback slowly reshapes a galaxy over billions of years. To the galaxy itself, such civilizations would be smaller than sparks. Meanwhile, the central black hole continues waiting patiently in darkness, and eventually, for many galaxies, another major transformation arrives. Not from black holes this time, but from collisions with entirely different galaxies drifting through the cosmos toward them. When people hear the phrase galactic collision, they usually imagine catastrophe. Entire star systems smashing into one another, planets thrown violently through space, galaxies exploding like cosmic car crashes across the universe. And to be fair, the name does sound alarming. If two galaxies each containing hundreds of billions of stars are heading toward each other, surely something unimaginably destructive must happen. But the reality is stranger and quieter. Galactic collisions are both less violent and more transformative than most people expect. In fact, some galaxies survive collisions surprisingly well. Others emerge completely changed. Some experience temporary rebirth. Others accelerate toward old age much faster than they otherwise would have. Which means a galactic collision is not always death exactly. Sometimes it is more like forced evolution. To understand why, we first need to appreciate just how empty galaxies really are. Science fiction often portrays galaxies as densely packed regions crowded with nearby stars. But actual interstellar distances are enormous beyond ordinary comprehension. If the Sun were the size of a grain of sand, the nearest star would still be several kilometers away. Stars inside galaxies are separated by huge stretches of emptiness. This means that when galaxies collide, direct stellar collisions are surprisingly rare. Not impossible, certainly, but statistically uncommon. Most stars simply pass by one another without impact. The real violence happens elsewhere. Gas clouds collide. Gravity reshapes trajectories. Entire galactic structures distort under tidal forces. And this process unfolds slowly over hundreds of millions or even billions of years. The word collision almost feels misleading because galaxies do not slam together instantly. They gradually interpenetrate, stretch, twist and merge like enormous gravitational weather systems. Picture two clouds drifting into one another across a very slow sky. At first, the galaxies approach quietly. Gravity begins pulling on outer stars and gas clouds long before the main bodies overlap. Spiral arms distort. Long, tidal tails stretch outward into space. Material gets pulled into enormous arcs spanning hundreds of thousands of light years. Even before the actual merger begins, both galaxies already look different. Astronomers observe these interactions all across the universe. Some of the most spectacular examples include the Antennae galaxies, two colliding spirals tangled together in brilliant streams of stars and gas. Huge regions inside them blaze with intense star formation, triggered by the merger itself. And that is where things become especially interesting. Collisions can briefly make galaxies more alive. As gas clouds crash together, they compress dramatically. Pressure rises. Gravity gains the advantage. Entire regions collapse into bursts of star formation. New stars ignite everywhere. Massive blue stars appear in huge numbers. Supernovae eventually follow. The galaxy becomes brighter, more energetic, more chaotic. A collision can trigger a cosmic baby boom. For a while, the galaxy experiences renewed activity on enormous scales. This is why astronomers sometimes describe mergers as starburst events. the rate of stellar birth surges far beyond normal levels. Some colliding galaxies produce stars hundreds of times faster than the Milky Way currently does. The universe becomes busy there again, violently productive, and yet this rebirth carries a hidden cost. Starbursts consume fuel rapidly. The merger burns through enormous quantities of cold gas in relatively short cosmic intervals. Massive stars formed during the burst die quickly and inject huge amounts of energy back into surrounding space. Supernova explosions heat remaining material. Central black holes may awaken as gas funnels inward toward galactic cores. The collision creates temporary abundance while simultaneously undermining long-term sustainability. It's rather like spending an entire savings account during one extravagant celebration. For a while, everything becomes brighter than ever. Afterward, exhaustion arrives. Many astronomers believe this is one of the major pathways through which galaxies age into giant elliptical systems. Two spiral galaxies merge. Star formation surges. Black holes activate. Gas gets consumed or heated. Eventually the chaos settles. The elegant spiral structure disappears. What remains is often a large elliptical galaxy populated mostly by older stars, with relatively little cold gas left for future generations. The collision both rejuvenated and accelerated aging at the same time. Death and rebirth tangle together, and this may very well be the future of the Milky Way. Right now, the Andromeda Galaxy is moving toward us at roughly 110 kilometers per second. That sounds fast because it absolutely is. Even so, the actual merger remains about 4 to 5 billion years away. Human beings tend to panic slightly at the phrase, "Our galaxy is colliding with another galaxy," but honestly, the timeline makes it difficult to feel immediate concern. You still probably have time to finish your tea. When the merger finally begins, the night sky from Earth, assuming Earth still exists in recognizable form by then, would become extraordinary. Andromeda would gradually grow larger over millions of years. Eventually it would dominate huge portions of the sky. Tidal distortions would reshape both galaxies. Streams of stars would arc overhead. The heavens themselves would appear to unravel and reform. Yet even then, the solar system would most likely survive physically intact. Again, stars are simply too widely separated for direct impacts to be likely. The real transformation happens on galactic scales. Over time, the Milky Way and Andromeda will lose their spiral identities entirely. Their structures will blend together through repeated gravitational interactions. Gas clouds will collide and compress. Star formation will intensify temporarily. Then the system will settle into something new. Astronomers sometimes jokingly call this future galaxy Milkomeda, which sounds less like a majestic cosmic object and more like a probiotic yogurt brand from the future. Still, the nickname captures an important truth. Galaxies are not fixed identities. They evolve through interaction. The Milky Way we know today is almost certainly the product of earlier mergers too. Astronomers have discovered streams of stars moving through our galaxy that appear to be remnants of smaller galaxies consumed long ago. Our galaxy grew partly through cosmic cannibalism. And Andromeda likely did as well. Large galaxies are built from countless earlier interactions layered across cosmic history. One especially fascinating aspect of galactic collisions involves how slowly the process unfolds compared to human intuition. Imagine if continental drift happened fast enough to watch directly. Coastlines would visibly reshape themselves across generations. Mountains would rise before civilizations. Galactic mergers are similarly dynamic, just stretched across vastly longer timescales. Entire intelligent species could emerge and disappear during a single merger phase, while the galaxies themselves barely finish rearranging their outer arms. The universe performs its greatest transformations patiently. And there is another strange emotional quality to galactic collisions. Despite their violence, they often produce extraordinary beauty. Long tidal tails glow across intergalactic space. Starburst regions blaze blue-white with newborn stars. gas clouds twist into intricate structures illuminated by radiation and supernovae. Some of the most visually stunning objects in astronomy are colliding galaxies, which says something curious about nature generally. Creation and destruction often happen together. The collision dismantles old structures while simultaneously triggering new stellar birth. And this duality makes galactic mergers difficult to classify neatly as either life or death. For some regions, the merger is catastrophic. Planetary systems destabilize, gas gets stripped away, star formation eventually shuts down. For others, the merger creates entirely new opportunities, fresh stars, fresh planets, potentially even fresh habitats for future life. The universe does not really separate endings and beginnings as cleanly as humans prefer. One process often becomes the doorway to another, and eventually, after enough mergers, galaxies lose much of their original structure altogether. Spiral galaxies depend partly on organized rotational motion. Repeated collisions disrupt that order. Stellar orbits become more randomized. The galaxy grows rounder and smoother. Elliptical galaxies emerge. These systems are fascinating because they often represent the later stages of galactic evolution. Many contain ancient stellar populations with little ongoing star formation. Their brightest years may already lie billions of years behind them, yet they are still enormous, still luminous, still drifting majestically through space. A dead or aging galaxy does not become ugly. If anything, some become even grander visually. Massive elliptical galaxies dominate the centers of galaxy clusters like ancient cosmic kingdoms surrounded by smaller companions. And at their centers sit enormous supermassive black holes, often grown larger through repeated mergers of earlier black holes during galactic collisions. Everything accumulates. Gravity keeps score patiently. One particularly strange consequence of galactic mergers involves black hole interactions themselves. When galaxies merge, their central black holes eventually begin orbiting each other. Over immense timescales, they spiral closer through gravitational interactions with surrounding stars and gas. Finally, they collide. The resulting merger releases tremendous amounts of energy through gravitational waves, ripples in space-time itself travelling outward across the universe. Humanity only recently detected gravitational waves directly for the first time, yet the cosmos has been producing them throughout its entire history. The universe is full of invisible motion and sound beyond ordinary perception. Future black hole mergers during galactic collisions may become some of the largest gravitational events in cosmic history, and after all the chaos settles, the galaxy remains altered permanently. Less gas, older stars, larger black holes, different structure. The collision becomes part of its biography, which brings us back to the original question. Are galactic collisions death or rebirth? The answer seems to be both. A collision can briefly revive star formation while simultaneously accelerating long-term decline. It can create enormous beauty while dismantling old structure. It can generate new stars and future worlds while exhausting the resources needed for future generations afterward. The universe rarely chooses simple categories. Galaxies especially resist them, and perhaps that complexity feels strangely familiar, because living systems on every scale behave similarly. Forest fires destroy ecosystems while creating conditions for new growth. Biological extinction events reshape life while opening evolutionary opportunities. Nature often transforms itself through disruption. Galaxies are no exception. Still, eventually even mergers stop helping. The available gas dwindles too far. The universe expands too much. Fresh interactions become rarer. Star formation slows permanently. The galaxy settles into older, quieter forms. Up to this point, we've talked about galaxies aging, slowing down, running out of cold gas, losing the ability to create new stars. But there's a deeper and stranger question waiting underneath all of that. Could a galaxy ever truly die completely? Not merely become old or quiet, not just stop forming stars, but actually reach a state where almost nothing recognizable as a galaxy remains at all? And the unsettling answer is yes. Eventually, given enough time, even the enormous structures we call galaxies begin to unravel. The important phrase there is given enough time, because once again the universe operates on scales so large that ordinary language starts struggling to keep up. Human civilizations measure history in centuries. Astronomy measures galactic aging in billions of years. The complete fading of galaxies may require spans so immense that even trillions of years become only the beginning of the story. Still, the process appears unavoidable, because galaxies are not permanent objects. They are temporary arrangements of matter held together by gravity and sustained by energy flow. And eventually both of those things begin working against long-term survival. The first stage of galactic death, as we've already seen, is the ending of star formation. Cold gas disappears. Young stars stop appearing. The galaxy becomes dominated by older stellar populations. At that point, however, the galaxy still absolutely exists. It remains bright with long-lived stars. Stellar remnants orbit through its structure. Black holes persist at the centre. From a distance, it may still look majestic. The real question is what happens afterward. What happens once the stars themselves begin disappearing too? Because stars do not last forever. Even the smallest red dwarfs, those astonishingly patient little stars capable of surviving trillions of years, eventually exhaust their fuel. And once the final stars die, galaxies enter a phase unlike anything the current universe has yet experienced. Astronomers sometimes call this the degenerate era, which sounds less like a scientific epoch and more like a jazz club hidden behind a suspicious alleyway. Still, the name exists for a reason. During this era, ordinary shining stars become rare or vanish entirely. Galaxies fill instead with stellar remnants, white dwarfs, neutron stars, black holes, cold dead objects drifting through darkness. The galaxy still possesses mass and structure, but the bright living phase has ended. And this transition happens incredibly slowly. Picture a dead galaxy 100 trillion years from now. The brilliant blue stars are long gone. Sun-like stars vanished ages earlier. Only the dimmest red dwarfs survive in scattered regions. Most of the galaxy consists of ancient remnants orbiting silently through cold space. The night sky inside such a galaxy would look profoundly different from ours. No glowing nebulae, no bright spiral arms, no crowded starfields rich with newborn suns. Just isolated faint stars separated by enormous darkness. Yet even then, the galaxy still technically exists. Gravity continues holding the structure together, and gravity is remarkably stubborn. That stubbornness matters because galaxies are not destroyed quickly once star formation ends. Their real dissolution happens through an entirely different process called gravitational relaxation. Over immense timescales, stars and remnants inside a galaxy constantly tug on one another through tiny gravitational interactions. Most encounters are weak. A slight orbital adjustment here, a small velocity change there, nothing dramatic. But given enough time, these countless interactions accumulate. Some objects gain energy and move into wider orbits. Others sink inward toward the galactic center. Eventually, certain stars and remnants acquire enough velocity to escape the galaxy entirely. The galaxy slowly evaporates. Not thermally, of course, gravitationally. Objects leak away one by one across unimaginable spans of time. Imagine a crowd gathered in a large hall where people occasionally bump into one another randomly. Most remain inside, but every so often somebody gets nudged hard enough toward the exit that they leave permanently. Now stretch that process across quadrillions of years. That is roughly how galaxies begin dissolving after their stellar eras end. And the process accelerates in some ways, because galaxies become increasingly dominated by dark compact objects. Black holes especially grow more important over time. When ordinary stars vanish, black holes remain among the most massive surviving objects. Their gravitational influence gradually reshapes the dead galaxy. Some drift toward the centre, others form binary systems. Occasionally, black holes collide and merge, releasing gravitational waves that carry energy away from the system. These mergers can even kick the resulting black hole outward at enormous speeds. In some cases, entire black holes may get ejected from galaxies altogether. The dead galaxy becomes increasingly chaotic in slow motion, aging matter rearranging itself endlessly in darkness. One particularly fascinating possibility involves stellar remnants interacting long after normal star formation has ceased. White dwarfs, for example, may occasionally collide. Normally, white dwarfs are stable cooling remnants left behind by stars like the Sun. But under certain conditions, collisions or mergers between them can trigger renewed fusion explosions. Tiny, isolated bursts of light briefly interrupting the darkness of dead galaxies. Even in cosmic old age, the universe may still produce occasional fireworks. Rare, scattered, lonely, but not entirely absent. There is something strangely emotional about that idea. A nearly dead galaxy still producing isolated flashes of activity across incomprehensible spans of silence, like embers occasionally flaring inside an ancient fire. Eventually, though, the larger trend wins. More objects escape, more black holes merge, more remnants cool, the galaxy's structure weakens, and another factor begins making things worse: the expansion of the universe itself. Right now, galaxies remain grouped together because gravity overcomes cosmic expansion locally. The Milky Way and Andromeda, for example, are moving toward each other despite the overall expansion of space. But on larger scales, galaxies drift farther apart over time. Dark energy drives this expansion faster and faster. As trillions of years pass, galaxies outside local gravitational groups disappear beyond the observable horizon entirely. Light from them can no longer reach surviving observers. Future civilizations, if any remain, may see only their own local dead galaxy surrounded by blackness. No visible evidence of the wider universe. Isolation becomes permanent, and this isolation affects galactic survival too. Fresh material stops arriving. New mergers become rare or impossible. The galaxy becomes a closed aging system with finite resources. Nothing rejuvenates it anymore. No new hydrogen flows inward from cosmic filaments. No neighbouring spirals drift close enough to interact meaningfully. The galaxy is left alone with its remnants. And then there is perhaps the strangest phase of all: black hole domination. Over extraordinarily long time scales, many surviving objects eventually get captured or disrupted by black holes. Central supermassive black holes may continue growing gradually as stars and remnants wander too close. Dead galaxies slowly feed their centres. The irony is extraordinary. The same black holes that helped suppress star formation earlier may become the final major structures remaining later. At this stage, a galaxy barely resembles what humans currently imagine when hearing the word galaxy. No bright spiral structure, no active stellar nurseries. Mostly dark remnants orbiting enormous black holes through expanding emptiness. And yet even this is still not the true end. Because black holes themselves are temporary, that remains one of the strangest discoveries in modern physics. Stephen Hawking showed that quantum effects should allow black holes to emit tiny amounts of radiation. Over incredibly long periods, black holes lose energy and slowly evaporate. Small black holes disappear faster. Supermassive black holes take almost absurdly long. A stellar black hole might survive for around 10 to the power of 67 years. Supermassive black holes may last closer to 10 to the 100th power years or beyond. Trying to picture those timescales is almost impossible. If every second since the Big Bang were represented by a grain of sand, you would still not come remotely close to such numbers. Human language becomes decorative at this point more than descriptive. Still, eventually, even the largest black holes evaporate, slowly, patiently. The galaxy loses its final anchors, and once the black holes are gone, something remarkable happens. the galaxy effectively ceases to exist as a meaningful structure, not because every particle disappears, but because gravity no longer holds the remnants together effectively. Matter becomes scattered and isolated across enormous distances. The organized system dissolves. What remains is not really a galaxy anymore, just lonely particles and cold remnants drifting through expanding space. And perhaps the strangest thing about this entire story is how gentle most of it sounds. Human beings instinctively imagine endings dramatically. We expect explosions, collapse, sudden catastrophe. The universe often prefers exhaustion instead. Galaxies do not usually scream as they die. They fade, their activity slows, their stars age, their structure loosens gradually across spans so immense that slow stops meaning much. There is no final moment where a cosmic voice announces the end of a galaxy. No ceremony, no curtain falling, only increasing quiet. In a way, galaxies die similarly to civilizations or ecosystems, not from one single cause, but from many overlapping changes accumulating over time. Fuel disappears, renewal stops, old structures dominate, energy spreads thinner and thinner, until eventually the system no longer resembles what it once was. And perhaps that is why the death of galaxies feels oddly moving despite the enormous scales involved. These are the largest organized structures most humans ever emotionally connect with in astronomy. They feel permanent because they outlive stars, planets, species, and civilizations. Yet even galaxies are temporary. Even galaxies age. Even galaxies eventually fade into the long, future darkness waiting for the universe itself. When we look at a galaxy through a telescope, it seems almost straightforward at first. You see the stars. You see glowing clouds of gas. You see spiral arms curving outward through darkness like enormous luminous storms frozen in slow motion, and naturally the human brain assumes that what we see is what exists. But galaxies are deceptive. What telescopes reveal is only a tiny fraction of the actual structure holding them together. Most of a galaxy is invisible, not hidden exactly. Invisible in a deeper and stranger sense. It does not emit light. It does not reflect light. It does not absorb light in ways we can easily detect. And yet without it, galaxies would not exist in their current form at all. This mysterious substance is what astronomers call dark matter. And although we still do not know exactly what it is, we know something important about what it does. It acts like the invisible skeleton of the universe, especially for dying galaxies. In fact, one of the strangest truths in astronomy is this. Long after the bright visible parts of galaxies begin fading away, dark matter remains quiet, massive, patiently holding structures together from the shadows. To understand why dark matter matters so much, imagine spinning a bucket of water overhead. As long as the bucket moves fast enough, the water stays inside because the motion balances gravity. Galaxies work somewhat similarly. Stars orbit the galactic center at tremendous speeds. The Milky Way itself rotates constantly, with our solar system moving around the galactic core at roughly 828,000 kilometers per hour. That is astonishingly fast, and yet galaxies remain stable, which immediately creates a problem, because when astronomers measured how quickly stars orbit galaxies, they discovered something deeply confusing. There was not enough visible matter to hold galaxies together. Stars near the outer edges of galaxies were moving far too quickly. According to ordinary gravity calculations based only on visible matter, those outer regions should have drifted apart long ago, but they did not. Something unseen was providing additional gravity. Something massive surrounded galaxies beyond what telescopes could directly observe. At first, astronomers suspected errors in measurement, but as observations improved, the evidence became overwhelming. Galaxies appear embedded inside gigantic halos of invisible matter. These halos extend far beyond the visible stars themselves. The Milky Way's visible disk spans roughly 100,000 light-years. Its dark matter halo may stretch more than 1 million light-years across. That means the galaxy humans recognize visually is only the bright central region inside a much larger invisible structure. Rather like seeing only the glowing filaments inside an enormous transparent jellyfish drifting through space. And dark matter dominates the mass budget completely. Ordinary visible matter, stars, gas, planets, dust, people, trees, teacups, everything familiar, makes up only a small fraction of the total matter in the universe. Most matter appears dark. Which is a wonderfully unsettling thing to realise before bed. Human beings evolved to trust visible reality, yet the cosmos itself is largely constructed from something we cannot directly see, and dying galaxies reveal this especially clearly. During active galactic life, bright stars dominate our emotional attention. Spiral arms blaze with light, star-forming regions glow beautifully, supernovae erupt. The galaxy feels alive because luminous processes overwhelm everything else visually. But as galaxies age and star formation slows, the visible portion gradually fades. The dark matter halo does not. In some sense, old galaxies become increasingly honest about what they truly are. Not bright islands floating independently through space, but luminous decorations embedded inside vast invisible gravitational frameworks. The stars were always only part of the story. One fascinating consequence of dark matter involves galactic survival itself. Remember earlier when we discussed how galaxies slowly evaporate through gravitational interactions? Stars and stellar remnants occasionally gain enough energy to escape the galaxy entirely. Without dark matter, this process would happen much faster. The dark matter halo acts like an enormous gravitational net extending far beyond the visible galaxy. It helps hold stars in orbit even as the galaxy ages. Long after spiral arms fade, the halo remains, quietly preserving structure. This becomes especially important during galactic collisions. When galaxies merge, their dark matter halos interact first, long before the visible disks fully overlap. In fact, much of the gravitational choreography during mergers is controlled by invisible mass rather than visible stars. Two galaxies approaching each other are really two enormous dark matter structures slowly interpenetrating. The stars merely trace the motion afterward like glowing dust caught in deeper currents. And after collisions settle, the resulting galaxy often inherits a larger combined dark matter halo surrounding the merged system. The invisible skeleton grows alongside the visible body. There is something strangely eerie about that image. Ancient dying galaxies floating through space wrapped inside enormous unseen structures extending vastly beyond their fading stars. The visible galaxy ages. The invisible framework persists. One of the clearest demonstrations of dark matter's reality came from observations of galaxy clusters, especially a famous system called the Bullet Cluster. Two galaxy clusters collided there long ago. The visible gas clouds interacted violently and slowed down through collision. But gravitational measurements revealed that most of the mass passed straight through largely unaffected. The invisible matter separated from the ordinary matter. It was one of the strongest pieces of evidence that dark matter is something physically real, rather than merely a misunderstanding of gravity. And that realization changes how we think about galactic death. Because galaxies are not just collections of stars gradually fading over time. They are visible expressions of much larger invisible systems. Even after most stars disappear, dark matter halos remain drifting through the cosmos. And they may survive astonishingly long, much longer than luminous structures themselves. Picture a galaxy trillions of years in the future. The spiral arms vanished long ago. Only dim red dwarfs and stellar remnants remain scattered through darkness. Black holes drift silently through old orbital paths. The galaxy's visible identity has mostly dissolved. Yet surrounding all of this, the dark matter halo still extends outward across enormous distances. invisible gravity continuing its patient work. There is something almost ghost-like about that future. A galaxy's skeleton outliving its light. Astronomers still do not know exactly what dark matter is made of. That remains one of the biggest unsolved problems in modern physics. It does not behave like ordinary atoms. It rarely interacts with normal matter except gravitationally. It passes through galaxies almost unnoticed. Various theories exist. Some scientists suspect entirely new kinds of particles. Others explore modifications to gravity itself. Experiments deep underground continue searching for evidence. So far, the universe remains stubbornly quiet about the answer, and perhaps that uncertainty adds another layer of strangeness to dying galaxies. Their survival depends heavily on something humanity still barely understands. The visible universe rests on invisible foundations. Even more fascinating is the possibility that dark matter influenced galactic birth from the very beginning. Current cosmological models suggest dark matter halos formed early after the Big Bang. Ordinary gas then fell into these gravitational wells, eventually forming stars and galaxies. If that picture is correct, then dark matter shaped both the birth and death of galaxies alike. It created the gravitational scaffolding necessary for galaxies to emerge. Then later, it helped preserve those structures long after their youthful stellar eras faded, invisible from beginning to end. One particularly haunting implication involves the far future universe. Eventually, ordinary luminous matter becomes increasingly rare. Stars die, galaxies fade, black holes evaporate over unimaginable timescales. Dark matter may remain among the dominant surviving forms of structure long after visible cosmic history ends. Though even that depends on what dark matter truly is. Some theories suggest dark matter particles themselves might eventually decay. If so, the invisible skeletons of galaxies may not be eternal either. The universe seems deeply resistant to permanence. Everything changes eventually. Still, during the long decline of galaxies, dark matter remains one of the great stabilizing forces preventing rapid collapse or dispersal. Without it, galaxies might never have formed properly. Without it, old galaxies might dissolve much faster. And this creates a curious emotional reversal. Humans instinctively focus on the bright visible stars because they feel important. Yet the invisible component may actually matter far more for the galaxy's long-term structure. The visible galaxy is almost like weather moving across a deeper landscape. Beautiful, dramatic, temporary. Meanwhile, the dark matter halo persists underneath with immense patience. There's something philosophically unsettling about that. The universe repeatedly reveals that the things humans notice first are often not the things truly shaping reality most deeply. Earth feels stationary despite racing through space. Solid matter feels stable despite being mostly empty space at atomic scales. Galaxies feel bright and luminous despite being dominated by invisible matter. Reality continually turns out stranger than our intuition expects, and dying galaxies expose this especially clearly, because as the luminous activity fades, the hidden framework becomes more conceptually important. The stars age, the gas disappears, the spiral arms dissolve, yet the invisible skeleton continues holding the remnants together, at least for a while. Because eventually even dark matter halos cannot prevent the broader fate waiting for galaxies. Gravity may hold systems together locally, but the universe itself continues changing on larger scales. Expansion accelerates, distances grow, isolation deepens, and over immense stretches of future time, galaxies do not merely age internally. They begin losing contact with the wider cosmos altogether. If you search the universe for a truly dead galaxy, not just an aging one, but a system that had largely exhausted its ability to renew itself, you might be surprised by how peaceful it looks. No shattered ruins drifting through chaos. No enormous explosions consuming entire star systems. No dramatic cosmic funeral. Most dead galaxies are strangely beautiful, calm, smooth, and quiet, in a way that almost hides what has happened inside them. In fact, If you showed many dead galaxies to someone unfamiliar with astronomy, they might assume those systems were the healthiest and most stable objects in the universe. Because galactic death does not usually look violent, it looks old. That distinction matters. When astronomers study galaxies actively forming stars, they often see cluttered structures filled with bright blue regions, tangled gas clouds, dark dust lanes, and uneven spiral arms glowing with youthful energy. Young galaxies can look messy, chaotic, busy. Dead galaxies often appear cleaner, more settled, like enormous cosmic cities after everyone loud has finally gone home. The most common shape for a dead galaxy is an elliptical galaxy. These systems lack the graceful spiral arms people usually associate with galaxies like the Milky Way. Instead, they appear smooth and rounded, with stars distributed in broad glowing halos. Some are nearly spherical, others look stretched like giant luminous footballs drifting through darkness, and inside them, the stellar population is overwhelmingly old. That is the key visual signature. Not destruction, aging. Imagine visiting a forest where no young trees have appeared for thousands of years. The forest would still exist, ancient trunks would still stand, but something essential would feel missing. That is roughly what astronomers see in dead galaxies. The youngest stars are gone, and without young stars, galaxies lose much of their energetic appearance. Young stars, especially massive blue stars, are extraordinarily bright. They dominate galactic light even though they represent only a tiny fraction of total stellar populations. But these stars live fast and die quickly. Once star formation stops, they vanish relatively soon on cosmic timescales. Within a few 100 million years, most of the brilliant blue light fades away. What remains are older stars, cooler stars, redder stars. This is why dead galaxies often glow with warm yellow-orange light instead of brilliant blue-white colour. The galaxy has entered its elderly phase. Astronomers sometimes describe these systems as red and dead, which sounds slightly rude honestly, especially considering some of them remain among the most massive structures in the universe. Still, the phrase captures something important. The redness signals old stellar populations. The dead part refers not to complete disappearance, but to the ending of meaningful star formation. The galaxy still contains stars, sometimes trillions of them, but almost no new ones are arriving. One particularly fascinating thing about dead galaxies is how quiet they become. Active galaxies are noisy places by cosmic standards. Supernovae explode regularly. Giant molecular clouds collapse. Radiation floods star-forming regions. Massive stars produce intense stellar winds. Dead galaxies lose much of that activity. Supernova rates decline dramatically because the short-lived massive stars already disappeared long ago. Nebulae become rare. Dust lanes fade. The overall environment stabilizes into something calmer and less turbulent. The galaxy becomes dynamically mature. There's something oddly comforting about that image. Not because galactic death is cheerful exactly, but because the universe seems to prefer gradual transitions over dramatic endings. A dead galaxy is not usually a destroyed galaxy. It is a galaxy that has simply stopped changing quickly. And yet beneath that calm appearance, strange things continue happening. The stars inside elliptical galaxies move differently than those in spirals. In the Milky Way, stars generally orbit in organized rotational patterns around the galactic center. Spiral galaxies resemble enormous spinning disks. Elliptical galaxies are more chaotic internally. Stars move in many different directions through the galaxy, rather than following neat circular orbits. This happens partly because many elliptical galaxies formed through ancient mergers. Repeated collisions scrambled the orderly motions that once supported spiral structure. The galaxy settles into a more randomized configuration, like a crowd dispersing after a long event. The visible result is smoothness. No spiral arms, no obvious structure, just vast stellar halos glowing softly through space. and some of these galaxies are absolutely gigantic. The largest known elliptical galaxies stretch across millions of light years and contain trillions of stars. They often sit at the centres of galaxy clusters surrounded by smaller companion galaxies, ancient cosmic monarchs ruling over crowded regions of space. One especially famous example is Messier 87, the massive elliptical galaxy whose central black hole humanity imaged directly for the first time. M87 looks serene through telescopes, smooth, golden, stable, but at its centre lurks a black hole containing billions of solar masses, launching enormous jets of energy into surrounding space. Even dead galaxies still contain hidden violence occasionally. It's just less visible than before. Another strange characteristic of dead galaxies is the absence of cold gas. This is one of the clearest differences astronomers measure. Young active galaxies contain huge reservoirs of hydrogen capable of forming future stars. Dead galaxies possess far less usable gas, and much of what remains is often extremely hot. This hot gas creates enormous halos surrounding some elliptical galaxies. X-ray telescopes reveal these giant clouds extending far beyond visible stars. The galaxy becomes wrapped in heated plasma drifting through invisible dark matter structures. Cold, dense molecular clouds, the birthplaces of stars, become increasingly rare. And once those clouds disappear, something psychologically important changes too. The galaxy loses its future. That sounds dramatic perhaps, but astronomically it is fairly accurate. Without star formation, no major new planetary systems appear. No young stars illuminate fresh nebulae. No large-scale renewal happens anymore. The galaxy enters a finite aging process. Every visible star belongs to an earlier era. One especially haunting thought involves what the night sky might look like from inside a dead galaxy. Right now, Earth's sky still contains many young bright stars. Regions of the Milky Way glow faintly with unresolved stellar density. Nebulae shimmer through telescopes. Star clusters sparkle across darkness. Future skies inside dead galaxies would feel emptier. The brightest stars would already be gone. Massive blue stars disappear quickly after star formation stops, so future observers would mostly see older, redder stars dominating the heavens. The sky itself would age. There may also be fewer obvious constellations because stellar populations gradually disperse and change over immense timescales. The galaxy becomes dimmer and more diffuse, and eventually things grow stranger still. As trillions of years pass, even many ordinary stars disappear. White dwarfs accumulate. Black holes drift through the galaxy invisibly. Red dwarfs dominate surviving stellar populations because they live so astonishingly long. At that stage, a dead galaxy no longer resembles the bright, elegant systems humans currently admire in astronomy photographs. It becomes sparse, cold, ancient. The visible stars spread thinly through huge regions of darkness. Some astronomers speculate that future galaxies may contain more stellar remnants than active stars. White dwarfs, neutron stars, black holes, a graveyard illuminated only by a few stubborn survivors still burning hydrogen slowly. And through all of this, dark matter remains surrounding the galaxy invisibly. That part is especially eerie. Even after most luminous activity fades, the invisible gravitational skeleton continues extending far beyond the remaining stars. The galaxy's hidden structure outlives much of its visible beauty. One interesting misconception about dead galaxies is the assumption that they must be completely inactive. That is not entirely true. Occasional events still occur, stars may collide rarely, white dwarfs can merge. Black holes continue interacting gravitationally. Some central supermassive black holes occasionally flare if fresh material falls inward. Dead galaxies are not frozen, just slower, far slower. Human beings instinctively associate life with movement and death with stillness. But galaxies challenge that distinction because even dead galaxies remain dynamic over enormous spans of time. Stars continue orbiting. Gravity keeps reshaping trajectories. Black holes merge occasionally. The galaxy evolves quietly beneath its calm appearance. There is another reason dead galaxies often look smooth and peaceful. Dust disappears over time. In active spiral galaxies like the Milky Way, dark dust lanes crisscross the disk because fresh star formation constantly replenishes interstellar material. Elliptical galaxies lack much of this structure. Without ongoing stellar birth, less fresh dust enters circulation. The galaxy appears cleaner visually. Ironically, aging makes galaxies photograph better in some ways. Less clutter, more symmetry, a quietness mistaken easily for perfection. And perhaps that is the strangest emotional aspect of dead galaxies. They do not look tragic. If anything, they look majestic. The universe rarely marks endings the way humans expect. No collapsing ruins, no giant cosmic warning signs reading, "This galaxy has reached the end of its productive years." Just old light continuing to travel through space. Calmness replacing activity. And perhaps that calmness feels unsettling partly because it mirrors something familiar from human experience. Many systems appear most stable right after their most creative eras have ended. Civilizations sometimes preserve their grandest architecture after their periods of expansion are already over. Forests can seem most peaceful when old growth dominates and little new growth appears underneath. Galaxies perform this transition on scales so vast that the emotional pattern becomes almost philosophical. The universe ages quietly, not suddenly. And perhaps the most extraordinary thing of all is that humanity exists early enough in cosmic history to still witness galaxies during their active eras. The Milky Way still forms stars. The universe still glows with youthful systems. Galactic collisions still trigger brilliant bursts of creation. We inhabit a cosmos that remains busy and luminous. Future observers trillions of years from now may not be so fortunate. Their skies may contain only ancient fading galaxies drifting through increasing darkness. No bright starburst regions, no crowded galactic neighborhoods, only old light lingering stubbornly against the expanding night. There is a future waiting for the universe so enormous and so quiet that even the word future barely feels appropriate anymore. Human beings tend to imagine the cosmos as crowded because the night sky still contains stars. Galaxies still fill telescopic images. Light still travels relatively freely across enormous distances. But this busy universe is temporary, and eventually galaxies will not merely grow old, they will grow isolated, profoundly isolated. In many ways, the loneliest era in the universe begins not with destruction, but with distance. Right now, galaxies exist inside a vast cosmic web stretching across billions of light years. Clusters and superclusters connect through enormous filaments of matter, like glowing threads woven through darkness. The Milky Way belongs to a small collection called the Local Group. Andromeda is part of it too, along with dozens of smaller galaxies orbiting nearby. Beyond that lie larger structures, the Virgo Cluster, the Laniakea supercluster, immense regions crowded with galaxies drifting through expanding space. To human eyes, the universe still looks socially active, but hidden underneath everything is one of the strangest discoveries in modern cosmology. The expansion of the universe is accelerating, not slowing down, accelerating. That single fact changes the long-term fate of everything. When astronomers first discovered cosmic expansion in the early 20th century, many assumed gravity would eventually slow the process. After all, galaxies attract each other gravitationally. Perhaps the universe would expand more slowly over time, or even collapse eventually in some future big crunch. Instead, observations revealed something deeply unsettling. Expansion is speeding up. Some unknown phenomenon, usually called dark energy, appears to dominate the large-scale behavior of the cosmos. And because of dark energy, distant galaxies gradually move away from one another faster and faster as space itself expands. This does not mean galaxies are racing through space like cars driving apart on a highway. Space itself stretches between them. The distinction matters because it creates a bizarre consequence. At sufficiently large distances, galaxies recede from one another faster than light can bridge the expanding gap. Not because they locally break relativity, but because the space between them grows too rapidly, and eventually this isolates galaxies permanently. The universe slowly pulls itself apart into islands. Imagine standing on a shoreline while fog gradually thickens across the ocean. One by one, distant ships disappear beyond visibility. That is roughly what happens cosmically, except the fog is expanding space-time, and the ships are entire galaxies. Over the next hundreds of billions of years, galaxies outside the local group will drift farther and farther away. Their light becomes increasingly redshifted, stretched toward longer wavelengths as expansion grows. Eventually, many will become invisible altogether. Future observers may look into the sky and see no distant galaxies at all. That thought is genuinely astonishing. Humanity exists during one of the rare periods in cosmic history when the wider universe remains visible. Future civilizations may never know the cosmos was once crowded, and this transforms the emotional feeling of galactic death completely. Dead galaxies do not merely fade internally, they become trapped inside expanding loneliness. Eventually the Milky Way and Andromeda will merge into one larger galaxy, probably elliptical in shape after billions of years of gravitational interactions. Smaller nearby galaxies may merge into this structure too. The local group gradually consolidates itself, and then everything else leaves. Not physically in the ordinary sense, simply unreachable. Galaxies beyond the local group drift away until their light can no longer arrive. The observable universe shrinks. Not because the universe itself becomes smaller, but because less of it remains accessible. Future astronomers living trillions of years from now may believe their galaxy is the entire universe, and honestly, from observational evidence available to them, that conclusion might seem perfectly reasonable. No visible cosmic expansion, no detectable cosmic microwave background radiation, because it will have stretched beyond observability. No rich fields of distant galaxies scattered across the heavens, just one ancient galaxy floating through darkness. Imagine trying to reconstruct modern cosmology under those conditions. It might become nearly impossible. Future civilizations may never discover the Big Bang at all. In a strange way, we are cosmologically early enough to still witness the universe while it remains communicative, and communication between galaxies matters more than it first appears. Young universes are dynamic partly because interactions remain common. Galaxies merge, fresh gas flows along cosmic filaments. Gravitational encounters reshape structures continuously. The future universe becomes increasingly static because distances grow too enormous for meaningful interaction. Isolation settles over everything. There is something haunting about that progression. The universe does not simply grow colder, it grows lonelier. Inside ancient dead galaxies, this loneliness becomes overwhelming. Picture a civilization living around a stable red dwarf trillions of years from now. The galaxy surrounding them contains mostly ancient stars and stellar remnants. The bright blue stars disappeared ages ago. Nebulae are rare. New star formation no longer happens. And beyond their galaxy, nothing visible. Not because nothing exists, but because cosmic expansion has hidden it permanently. Their night sky would feel profoundly different from ours. Modern humans can look through telescopes and see thousands of galaxies in tiny patches of sky. Each one contains billions of stars. Future skies may contain only local ancient stars scattered across darkness. The wider universe effectively disappears. And as time continues passing, even local galaxies begin changing further. Stars slowly escape through gravitational interactions. Black holes merge. Stellar remnants accumulate. Ordinary luminous matter becomes rarer. The galaxy itself grows quieter internally, while external isolation deepens simultaneously. everything contracts emotionally towards smaller scales. One especially strange consequence of this future involves the concept of history. Right now, the universe still preserves visible evidence of its earlier eras. Astronomers can study distant galaxies and literally observe cosmic history unfolding because light requires time to travel. The farther away we look, the further back in time we see. Future observers lose that advantage. The visible archive disappears gradually. Ancient cosmic history becomes inaccessible. It's a little like a library burning down one shelf at a time until eventually only local records remain. The universe forgets itself visually. That may sound poetic, but physically it reflects something real. Cosmic expansion eventually destroys observational access to enormous portions of reality. Future astronomers may inhabit an observational prison built from space-time itself. And then there is the psychological aspect. Human beings evolved socially. We measure ourselves partly through relationships with larger systems around us. Civilizations likely do something similar cosmically. There is comfort in knowing the universe contains countless galaxies, clusters, and structures beyond our own. The far future removes that comfort. The cosmos becomes provincial. One galaxy, one local structure, darkness beyond. Even if intelligent life survives deep into this era, the emotional relationship between observers and the universe changes fundamentally. The cosmos no longer feels infinite in the same visible way. It feels abandoned. Still, stars continue burning for immense spans of time within these isolated galaxies, especially red dwarfs. And perhaps that makes the loneliness even sharper. The lights remain on long after the larger community has vanished. There is another deeply unsettling implication too. Communication between galaxies eventually becomes impossible forever. Right now, if humanity somehow developed sufficiently advanced technology, signals could theoretically reach nearby galaxies over immense timescales. In the far future, expansion prevents even light from bridging growing distances. Galaxies become causally disconnected. Permanent islands in an accelerating sea. This means the final civilizations of the universe, if any endure, may live entirely alone without possibility of discovering or contacting anything beyond their own ancient galaxy. No neighboring civilizations, no external galaxies, no future visitors. Only local remnants orbiting through darkness. And strangely enough, this loneliness emerges not because the universe runs out of matter immediately. It emerges because space-time itself changes the rules of connection. The cosmos becomes too large to remain socially coherent. There is something deeply human about finding that frightening. Perhaps because isolation feels like a kind of death on smaller scales too. Yet the universe does not experience loneliness emotionally. It simply evolves according to physical laws. Dark energy expands space, galaxies drift apart, light loses the race against growing distances, the cosmos becomes quieter, not cruelly, not intentionally, just gradually. And eventually, after enough time passes, even the isolated galaxies themselves continue fading. Red dwarfs die, white dwarfs cool. Black holes dominate more and more of the remaining structure. The ancient galaxy grows darker internally, while the outer universe remains unreachable forever. Still, one thing persists surprisingly long: motion. Even dead galaxies remain dynamic for unimaginable stretches of time. Stars orbit, remnants scatter, black holes interact gravitationally. The universe never becomes entirely frozen, just slower, colder, more silent. And perhaps silence is the defining feature of this era more than darkness itself. Young universes are noisy places by cosmic standards. Supernovae explode regularly, galaxies collide, quasars blaze, star formation erupts constantly across space. The loneliest era loses much of that activity. Fewer explosions, fewer collisions, fewer new beginnings. The universe gradually stops surprising itself. and perhaps that is why dying galaxies feel so emotionally different from dying stars. A star can die violently in one final blaze. Galaxies mostly fade into solitude. The lights diminish slowly while the distances between everything grow larger and larger forever. And eventually, after enough time passes even for the patient red dwarfs, the universe enters an age where ordinary stars themselves begin disappearing entirely. There is something deeply unsettling about realizing that the stars themselves are temporary. Human beings instinctively treat stars as symbols of permanence. Ancient cultures built mythologies around them. Sailors navigated by them. Entire civilizations measured time through their movements across the sky. Even now, modern people often look upward searching for stability among the stars because they seem immune to the ordinary fragility of life on Earth. Mountains erode, cities collapse, species disappear. But the stars remain. At least that is how it feels from a human perspective. Yet every star in the night sky is living on borrowed time. Some simply borrowed much more than others. And eventually, far beyond the eras of living galaxies and glowing nebulae, the universe enters a period where stars begin disappearing permanently. Not through sudden catastrophe, not all at once, but slowly enough that the darkness almost arrives unnoticed at first. This era begins after galaxies have already grown old. Star formation largely stopped long ago. Most cold hydrogen gas disappeared or became unusable. Bright blue stars vanished ages earlier. The universe settled into quieter rhythms dominated by smaller, longer-lived stars. At that stage, red dwarfs become the main surviving stars in existence. Tiny, cool, extremely efficient, and astonishingly long-lived. Right now, the universe is far too young for even one naturally formed red dwarf to have completed its full lifespan. Every red dwarf ever created still exists somewhere in the cosmos today. That fact alone is remarkable. Some of those stars formed over 13 billion years ago, shortly after galaxies themselves began taking shape. They are still quietly burning hydrogen right now, and may continue doing so for trillions of years more. The future belongs to small stars, at least for a while, and because of that, the transition toward cosmic darkness happens incredibly slowly. Picture a future galaxy hundreds of trillions of years from now. The great star-forming eras are ancient history. Spiral arms faded long ago. Most bright stars disappeared ages earlier. White dwarfs drift silently through darkness beside neutron stars and black holes. Yet scattered throughout this ancient galaxy, red dwarfs still glow. Dim red points suspended inside enormous darkness. The galaxy is old beyond comprehension, but not entirely dark. Not yet. This intermediate phase may last longer than every previous era of cosmic history combined. That's the strange thing about the future universe. Once large energetic stars disappear, time itself begins feeling different. Young universes change rapidly. Massive stars explode frequently. Galaxies collide. Quasars blaze. Star formation reshapes cosmic structure constantly. Old universes become patient. The remaining stars burn so slowly that major visible changes occur across intervals, difficult even for advanced civilizations to perceive directly. A red dwarf does not rush. Its fusion process is extraordinarily conservative. Large stars waste fuel quickly because immense gravitational pressure forces rapid fusion in their cores. Red dwarfs avoid that problem partly because they are so small. Their interiors remain fully convective, meaning hydrogen circulates throughout the star rather than staying trapped in isolated core regions. They can use much larger percentages of their available fuel. The result is astonishing longevity. Some may survive for 10 trillion years, others even longer. Trying to emotionally grasp those timescales is difficult because human minds evolved around lifespans measured in decades. 1 million years already feels ancient to us. 1 trillion years is something else entirely. If human history from the first cities until today were compressed into 1 second, 1 trillion years would still stretch for over 8 years continuously. And during much of that unimaginable span, red dwarfs continue shining, the last ordinary lights of the universe. Still, even they cannot burn forever. Eventually hydrogen reserves diminish. The smallest stars begin changing too. This is where astronomy becomes oddly speculative, because the universe has not existed long enough for anyone to directly observe these future stellar deaths. Scientists must model them mathematically. Current theories suggest many red dwarfs will gradually become hotter and brighter late in life, rather than dimmer immediately. Some may transform into what astronomers call blue dwarfs, stars that briefly grow more luminous before finally exhausting their fuel. Interestingly, no blue dwarfs exist yet because not enough time has passed. The future universe may therefore contain stellar types currently absent from reality altogether. Even cosmic old age invents new phenomena occasionally, but eventually the process reaches its unavoidable conclusion. Fusion ends. The star becomes a white dwarf. No more new energy production, only leftover heat slowly radiating into darkness. And once the red dwarfs begin disappearing, something profound changes in the emotional structure of the cosmos. Before this point, even dead galaxies still contain ordinary stars. Ancient stars perhaps, but recognizable lights similar to those humans know today. Afterward, the universe transitions into something colder and stranger. Ordinary starlight itself becomes rare. The skies of surviving civilizations, assuming any exist then, would feel almost impossible for modern humans to recognize emotionally. No bright constellations, no crowded Milky Way stretching overhead, no nearby star-forming nebulae glowing softly through darkness, just isolated remnants scattered through enormous blackness, white dwarfs, neutron stars, black holes, occasional dim red survivors still burning their final reserves. The universe loses its warmth gradually. One especially haunting aspect of this transition involves planets. During the active eras of cosmic history, stars constantly create new planetary systems. Young suns emerge surrounded by disks of dust and gas. Worlds form continuously throughout galaxies. Once star formation stops, the planetary inventory becomes fixed. No major new worlds appear. Every habitable environment belongs to an aging star. And eventually, as stars disappear one by one, planetary systems disappear with them. Some planets get swallowed during stellar expansion phases, others freeze after their stars die. Rogue planets drift loose into darkness through gravitational interactions. The universe slowly empties of living sunlight, yet not everything vanishes immediately. White dwarfs remain warm for long periods. Hypothetically, some future civilizations might survive around them using artificial energy systems or carefully managed orbital engineering. There are even theoretical discussions about life around red dwarfs lasting trillions of years. The future universe may therefore remain inhabited far longer than people usually imagine, but it becomes increasingly difficult. Energy grows scarcer, distances become larger. The cosmos stops offering fresh beginnings easily. And eventually another strange thing happens. The dominant visible objects in the universe stop being stars altogether. Stellar remnants take over. White dwarfs become especially common because stars like the Sun end this way. A white dwarf contains roughly stellar mass compressed into planetary size. Matter inside becomes extraordinarily dense, supported by quantum mechanical effects rather than ordinary gas pressure. At first, white dwarfs glow intensely hot. Over immense periods they cool gradually, and eventually they become black dwarfs. Cold dead stellar remnants no longer emitting significant light. No black dwarfs currently exist because the universe remains too young. Even the oldest white dwarfs still retain leftover heat from earlier stages. But in the far future, black dwarfs may become one of the most common objects in existence. Imagine galaxies filled mostly with cold dead stars invisible against darkness. That is where the universe eventually heads. And neutron stars persist too. These extraordinary objects form when massive stars collapse during supernova explosions. A neutron star contains roughly stellar mass compressed into a sphere only about 20 kilometers wide. Their density is almost absurd. A teaspoon of neutron star matter would weigh billions of tons on Earth. Some continue spinning rapidly while emitting beams of radiation as pulsars. Others cool slowly across unimaginable spans. And then there are the black holes. As ordinary stars disappear, black holes inherit more and more of the future universe simply because they survive longer than almost anything else. Galaxies gradually shift from luminous ecosystems into graveyards populated mostly by stellar corpses. The light loses its statistical dominance. Darkness becomes normal. What makes this transition especially strange emotionally is how gradual it remains. Human beings associate disappearance with sudden absence. A light bulb burns out instantly. A fire goes dark quickly. Stars disappear cosmically the way glaciers melt geologically, slow enough that every stage feels almost permanent while it lasts. And because the process unfolds across such enormous timescales, civilizations living during different eras might perceive the universe completely differently. Early civilizations, like humanity today, inhabit a bright, crowded cosmos rich with visible galaxies and active star formation. Far future civilizations may know only dim ancient stars scattered through near-empty skies. Still later civilizations, if any survive, may witness the final fading of ordinary starlight itself. Each era experiences a different universe, and perhaps the saddest part is that future observers may not even realize how extraordinary the earlier universe once looked. By the time stars begin disappearing permanently, evidence of cosmic youth has largely vanished already. Distant galaxies disappeared beyond the observable horizon long ago due to cosmic expansion. The cosmic microwave background faded beyond detectability. Star-forming regions became ancient history. The universe forgets its own beginnings visually. Future astronomers may struggle to reconstruct cosmic history because the evidence itself gradually disappears. In a strange way, the universe becomes less informative over time. And then there is the issue of entropy. Everything we have discussed ultimately traces back to one enormous physical trend. Energy spreads out. Useful structures become hard to maintain. Stars shine because they create imbalance, converting concentrated fuel into diffuse radiation. Once the fuel runs out, equilibrium slowly wins. The universe moves steadily toward less organized energetic states. Not because anything actively destroys order maliciously, simply because physical systems statistically drift that way over time. Stars are temporary victories against equilibrium, beautiful ones certainly, but temporary. Still, even as stars disappear, the universe does not become completely inactive immediately. Rare collisions still occur, and still. Black holes continue merging. White dwarfs occasionally interact catastrophically. Gravitational encounters slowly reshape old galaxies. Motion persists astonishingly long. But the emotional center of cosmic history changes once ordinary stars begin vanishing forever. The universe loses its familiar lights. By the time galaxies truly reach old age, black holes inherit the universe. Not suddenly, not dramatically. They simply outlast almost everything else. The bright stars disappear first. Massive blue stars vanish early. Sun-like stars follow billions of years later. Even the patient red dwarfs, those tiny stubborn stars capable of surviving for trillions of years, eventually exhaust their fuel too. Galaxies grow darker, colder, quieter, and through all of it, black holes remain. At first, they are only part of the cosmic story. Young galaxies are dominated visually by stars, nebulae, and brilliant regions of star formation. Black holes hide quietly in the background unless actively feeding. But the future changes the balance. As ordinary starlight fades away across the cosmos, black holes become increasingly important, simply because they survive so much longer than almost anything else. The far future universe may eventually belong more to gravity than to light. And nowhere is that transition clearer than inside ancient dead galaxies. Right now, humanity tends to imagine black holes as rare exotic objects. Fascinating, certainly, but unusual. That impression is misleading. The Milky Way alone likely contains millions of stellar black holes formed from ancient massive stars. Most drift invisibly through space, impossible to see directly unless they interact with nearby matter. And at the centre of our galaxy sits Sagittarius A star, the supermassive black hole containing roughly 4 million times the Sun's mass. Other galaxies contain even larger monsters. Billions of solar masses compressed into regions smaller than planetary systems. These black holes already shape galaxies today, but in the far future, they become some of the last major structures still actively influencing cosmic evolution. Picture a galaxy 1 quadrillion years from now. The bright spiral arms disappeared unimaginably long ago. Most stars are gone or transformed into remnants. The galaxy contains white dwarfs, neutron stars, rogue planets, and enormous numbers of black holes drifting through ancient gravitational orbits. Ordinary starlight is rare. Darkness dominates. Yet black holes still move patiently through this dying structure. The galaxy itself no longer resembles the Milky Way humans know today. It feels more like a graveyard held together by invisible gravity, and black holes become its largest surviving inhabitants. One especially strange thing about black holes is how emotionally misleading they are. People often imagine them as cosmic vacuum cleaners aggressively sucking in everything nearby. But most black holes spend the overwhelming majority of their existence doing almost nothing at all. A black hole sitting alone in empty space is practically invisible. It only becomes spectacular when matter falls toward it, and in the far future, matter becomes increasingly scarce. This means ancient black holes often drift through enormous darkness, with very little activity around them. Still, galaxies remain crowded enough for interactions to continue occasionally. Over immense timescales, gravitational encounters slowly reshape everything inside dead galaxies. Stars and remnants pass near black holes. Some objects get captured into orbit. Others wander too close and are torn apart by tidal forces. When matter falls into a black hole, even in the distant future, the old violence briefly returns. Accretion disks form, radiation erupts. The black hole glows again temporarily through the destruction of surrounding material. Imagine an ancient dead galaxy almost completely dark except for occasional bursts of light flaring around feeding black holes. Tiny, isolated pockets of brightness interrupting endless night. The universe never fully stops moving. It simply becomes quieter between events, and eventually black holes begin interacting with one another more frequently than with ordinary stars because black holes themselves become increasingly common relative to luminous matter. This changes galactic dynamics profoundly. Large black holes slowly migrate inward toward galactic centers through gravitational interactions. Smaller objects get scattered outward. Over unimaginable spans, many black holes sink into dense central regions. There, mergers begin happening. Two black holes orbit each other slowly at first. Gravitational waves carry energy away from the system. The orbit shrinks gradually, closer, closer. Finally, they collide. The resulting merger releases enormous bursts of gravitational radiation rippling across space-time itself. No explosion in the ordinary sense, no fire, just gravity shaking the structure of reality. Humanity only recently learned to detect gravitational waves directly, yet in the far future, black hole mergers may become among the most significant energetic events still occurring anywhere in the cosmos. Ancient galaxies continue producing invisible music long after ordinary starlight fades away, and the merged black hole survives, larger than before, more massive, more dominant. This process repeats countless times across deep future history. Galactic centers gradually accumulate enormous black holes through repeated mergers and captures. Some may eventually contain absurd amounts of mass concentrated into relatively small regions, the final monarchs of dead galaxies. Still, even black holes face limitations. There is only so much material left to consume. As stars disappear and remnants scatter, feeding opportunities decline. The ancient galaxy becomes increasingly empty. Eventually, black holes themselves begin encountering a strange problem: loneliness. Not emotional loneliness, of course. Physical isolation. Remember the accelerating expansion of the universe. Galaxies outside local gravitational groups disappeared beyond visibility long ago during these future eras. Dead galaxies drift alone through enormous darkness, with no fresh matter arriving from outside. The black holes inherit a closed system with finite resources, and over sufficiently long timescales, even galaxies themselves begin dissolving gravitationally. Stars escape. Remnants scatter. Interactions grow rarer. Matter spreads thinner and thinner across expanding space. The black holes survive, but the environments surrounding them become increasingly sparse. One fascinating possibility involves black holes capturing rogue planets or dead stellar remnants into stable orbits. Future civilizations, assuming any survive that long, might theoretically exploit energy from accretion processes around black holes themselves. Some physicists have even speculated about advanced civilizations living near rotating black holes to extract energy extraordinarily efficiently. The future universe may force intelligence, if it persists, toward increasingly strange habitats. Stars become unreliable eventually. Black holes may remain among the few usable long-term energy sources left. Though usable becomes a relative term when discussing timescales vastly exceeding current cosmic history. Still, the greatest surprise about black holes comes much later. They are not eternal. That realization changed physics profoundly in the 20th century. Originally, black holes seemed completely permanent. Gravity traps everything inside the event horizon forever. Nothing escapes. Then Stephen Hawking combined quantum mechanics with black hole physics and discovered something extraordinary. Black holes should slowly evaporate. Quantum fluctuations near the event horizon allow tiny amounts of energy to escape over time through what is now called Hawking radiation. The effect is incredibly weak for large black holes. A stellar black hole takes roughly 10 to the power of 67 years to evaporate completely. Supermassive black holes survive vastly longer still. Numbers here become almost comically large. Some may persist for around 10 to the power of 100 years. Trying to visualize that span meaningfully is almost impossible. If every atom in the observable universe represented 1 second, you still would not adequately represent such timescales. Human language was simply not built for this. Yet despite those immense durations, the conclusion remains unavoidable. Black holes lose energy gradually, slowly, patiently. The universe eventually even takes them too. And this creates one of the strangest emotional reversals in all of cosmology. Black holes begin as terrifying destroyers of stars. They end as the last fading survivors of cosmic history. The very objects once associated with endless darkness ultimately disappear into darkness themselves. As Hawking radiation removes mass, black holes shrink. Smaller black holes evaporate faster, so the process accelerates near the end. The final moments may produce bursts of radiation before the black hole vanishes entirely. No more event horizon, no more trapped gravity well, just energy dispersed into space. Imagine the last supermassive black hole in a dead galaxy, evaporating after unimaginable ages. By then, the galaxy itself barely exists as a coherent structure anymore. Most matter has scattered across enormous distances. Ordinary stars vanished long ago, even stellar remnants may be rare, and then the central black hole disappears too, the final anchor releases its grip. What remains afterward hardly resembles the universe humans currently know. No galaxies in the familiar sense, no stars, no nebulae, no bright skies, mostly isolated particles drifting through expanding darkness. The universe enters what physicists sometimes call the dark era. And yet even that name feels slightly inadequate, because dark suggests absence of light compared to some remembered brightness. The future universe may become so old that concepts like galaxies and stars feel almost mythological compared to surviving reality. Still, there is something oddly calming about the slowness of all this. Human beings fear endings partly because our endings happen quickly. Fires burn out in minutes, lives end in decades, civilizations collapse across centuries. The universe prefers patience, galaxies fade gradually, stars disappear one by one, black holes evaporate across timescales so vast they almost transform death into geology. Nothing hurries. And perhaps that is why thinking about black holes after the end of galaxies feels less frightening than expected. The cosmos does not crash violently into oblivion, it drifts there, slowly enough that each era feels complete while it lasts. Right now, humanity lives during one of the brightest and busiest chapters of cosmic history. Galaxies still blaze with young stars, black holes still feed actively in many regions, the universe remains crowded with structure and energy. Far future observers, if any exist, may inherit a cosmos almost unrecognizable by comparison, a universe where black holes are among the final surviving giants, wandering through ancient darkness. Eventually, the universe becomes so old that even the idea of a galaxy starts feeling historical. Not ancient in the way dinosaurs are ancient to humans, not ancient in the way pyramids or mountains are ancient, something far beyond that. A future so distant that the entire era of living galaxies, glowing nebulae and crowded star-filled skies becomes only a brief early chapter in cosmic history. And yet the strange thing is this: the universe does not end with a bang. It does not collapse dramatically into fire or explode outward into sudden destruction. Instead, it grows quieter, slower, darker, until eventually almost nothing recognizable remains from the cosmos we know today. By the time we arrive at the final cosmic silence, galaxies have already died long ago, star formation ended ages earlier, the last red dwarfs exhausted their fuel, white dwarfs cooled into black dwarfs, neutron stars drifted through darkness, black holes merged, evaporated, and disappeared across spans of time so enormous that ordinary words barely function anymore. The structures humans emotionally associate with the universe are gone. No Milky Way, no Andromeda, no glowing spiral arms turning through darkness. Even the giant elliptical remnants that once survived after galactic death have gradually dissolved through gravitational interactions and cosmic expansion. The universe loses its architecture, and what remains afterward is almost impossible to picture emotionally because human beings evolved inside a cosmos rich with structure and light. The night sky shaped human imagination from the beginning. Ancient people looked upward and saw patterns. Hunters navigated beneath stars. Sailors crossed oceans guided by constellations. Entire mythologies formed around the heavens because the sky appeared alive with motion and meaning. Even modern astronomy still studies a universe crowded with objects. Stars, galaxies, quasars, nebulae, clusters, supernovae. The future universe abandons nearly all of that. Eventually the cosmos enters an era where ordinary matter itself becomes sparse and isolated. And the strangest part is how empty the future becomes compared to the present. Right now, space already feels empty to human intuition. The nearest star beyond the sun sits over 4 light-years away. Galaxies are separated by millions of light-years. Huge regions of the cosmos contain almost nothing at all. Yet compared to the far future, the modern universe is unbelievably crowded, busy, energetic, alive with interaction. The final cosmic silence emerges after interaction itself becomes rare. That is the key transformation, because the universe does not merely lose light over time, it loses connection. As cosmic expansion continues accelerating, distances between surviving structures grow larger and larger. Long before the final stars disappear, galaxies outside local gravitational groups vanish beyond the observable horizon forever. The visible universe shrinks. Eventually, even dead galaxies themselves dissolve into isolated remnants, drifting through enormous darkness. The cosmos fragments. And once the black holes finally evaporate through Hawking radiation, something deeply important disappears with them. Large-scale organization. No major structures remain to gather matter gravitationally anymore. No stars creating concentrated energy. No galaxies shaping enormous regions of space. The universe becomes thin, cold, diffuse. A vast ocean of low-energy particles spread across expanding darkness. Physicists sometimes describe this final state using a phrase that sounds deceptively simple: heat death. The name can be misleading because the future universe is not especially hot. Quite the opposite, in fact. The phrase refers to thermodynamic equilibrium, a state where usable energy differences disappear, and energy differences are what make interesting things happen. Stars shine because their cores are hotter than surrounding space. Planets support weather because energy flows unevenly across them. Life exists because organisms exploit energetic imbalances continuously. The final universe approaches a condition where almost all major imbalances are gone. No concentrated fuel reserves, no large-scale gravitational collapse, no fresh star formation, no enormous energetic processes reshaping cosmic structure. The universe settles toward equilibrium, and equilibrium is quiet. One way to think about it is this. Imagine a room where a perfume bottle shatters in one corner. At first, the scent remains concentrated locally. Over time, however, molecules spread gradually through the room until the smell becomes evenly distributed everywhere. Once equilibrium is reached, nothing interesting happens anymore. The perfume molecules still exist, but the dramatic transition phase is over. The future universe behaves similarly with energy itself. Over unimaginable timescales, useful concentrations spread thinner and thinner. The cosmos smooths itself out. And perhaps the eeriest aspect of all this is that time itself begins losing meaning psychologically. Human beings experience time through change. Morning becomes evening, seasons shift, civilizations rise and fall, stars move across the sky. But what does time feel like in a universe where almost nothing changes anymore? The final cosmic silence may stretch across intervals so enormous and uneventful that ordinary ideas of history become difficult to apply. There are no more galactic eras, no more stellar generations, no more cosmic revolutions transforming the universe dramatically. Only sparse particles drifting through expanding space. The fascinating thing is that physics itself continues operating normally. Gravity still exists. Quantum mechanics still functions. The laws of nature remain. What disappears are the conditions required for complexity. The universe does not die because physics stops working. It dies because the opportunities for structure gradually run out, and that distinction makes the ending feel strangely gentle. No apocalypse, no final catastrophe. Simply exhaustion spreading slowly across reality. There is another profoundly strange possibility too. Some physicists speculate that protons themselves, the particles making up ordinary atomic matter, may eventually decay. This has never been observed directly, and proton decay remains hypothetical. But certain theories suggest ordinary matter itself might not be perfectly stable forever. If true, even the remaining atoms drifting through the future universe gradually disappear over astonishingly long timescales. Matter dissolves into radiation and lighter particles. The future cosmos becomes even thinner, even emptier. At that point, the universe contains mostly extremely low-energy photons, neutrinos, and isolated particles scattered across incomprehensible distances. The word lonely almost stops being adequate, and yet despite all this darkness, something remarkable remains true. The universe never becomes absolutely nothing. That distinction matters. Even during the final cosmic silence, existence continues. Space remains, time continues. Quantum fluctuations still occur. Reality itself does not vanish. The universe simply enters a condition where complexity and structure become extraordinarily rare. There is something deeply philosophical about that. Human beings often imagine endings as absolute. Stories conclude, fires go out, lives end. The cosmos prefers transformation instead. Every phase of the universe emerges from earlier phases and gradually transitions into something new. The bright stellar era arose from the hot, dense early universe. Galactic ages followed. The age of dying stars came later. Black holes inherited the future afterward, and eventually even they faded into the long equilibrium ahead. The universe never really stops, it just changes character. Still, emotionally, the final cosmic silence feels different because it represents the ending of everything familiar. No civilizations looking upward beneath stars. No planets orbiting warm suns, no galaxies glowing softly across intergalactic darkness. The cosmos loses its visible beauty gradually, and perhaps that realization makes the present universe feel more precious. Humanity exists during an extraordinarily lively era of cosmic history. The stars still shine, galaxies still form patterns across the heavens, black holes still blaze as quasars in distant regions. The night sky still carries evidence of ancient explosions, collisions, and births. We inhabit a universe rich with activity. Future observers, if any survive long enough, may inherit something unimaginably quieter, and in a strange way that gives modern existence a certain cosmic timing. Not special in a mystical sense, simply temporary. We arrived while the lights were still on. That thought changes astronomy emotionally. The Milky Way stops feeling eternal once you understand it has a lifespan. The stars overhead become participants in a larger story rather than fixed decorations suspended permanently above Earth. Everything joins the process eventually. Stars, galaxies, black holes, even the structure of the observable universe itself. Yet strangely enough, this realization does not necessarily make the cosmos feel meaningless. If anything, impermanence gives cosmic history shape. A universe where nothing changed would contain no stories at all. No stars would form, no planets would emerge, no chemistry would evolve into life. Complexity itself depends on temporary imbalances and transitions. The reason humans exist is precisely because the universe is not static. We are products of a cosmos still evolving, still moving, still burning through its great Middle Ages, and maybe that is the quiet comfort hidden underneath the story of dying galaxies. The universe does not fail because it changes. Change is what the universe has always done. Galaxies were never meant to last forever. They were phases. Beautiful phases, certainly. Enormous rotating cities of stars shining across deep time, but still temporary. One day the Milky Way will disappear. One day the last stars will fade. One day even the black holes will evaporate into darkness. And after all of that, the universe continues onward in silence. Vast, cold, almost empty, yet still existing. Still carrying the faint memory of everything that once burned brightly inside it. And for now, at least, humanity remains here during the luminous age, lying beneath living stars while galaxies still glow across the night sky.